So our first talk, our first lecture today will be given by Professor Pascal Van Hentenryck from Georgia Tech, where he is the director of the NSF AI Institute for Advanced Optimization, in addition to the AI Hub at Georgia Tech. So he'll be talking about AI for power system operations. So Pascal, the floor is all yours.
Yeah, merci Antoine. Toujours très honoré d'être au Canada. I'll switch to English in a moment. Merci beaucoup pour l'invitation. So again, delighted to be here in Montreal in this always amazing environment. So I'm going to talk about AI for power operations. I have about 240 slides that I did in the plane yesterday. So feel free to interrupt me at any time. I'm supposed to know what is in those slides, although there are so many that I don't remember some of them. So feel free to interrupt me at any time. I'm going to go slow and then stepping up as we go along and getting in more and more details. So this is my first slides because the next slide that I'm going to show you is a slide that I borrowed from one of our collaborators. So I'm going to steal a slide which I find very interesting. So this is a slide that I took from ERCOT. ERCOT is the transmission operator of Texas in the United States. Texas is a very interesting operator. They have a lot of wind, they have a lot of congestion, they have a lot of batteries, and they are one of the most innovative ISOs in the United States. And what they are telling at this stage, I'm not sure they were telling this 10 years ago, but that in the old times, everything was easy. You have dispatchable generation. You can control your generators the way you want. You had the load that was highly predictable. And in the middle, you were basically dealing with transmission and operators and distribution. And what you wanted to do is just maintain the frequency such that your system would work nicely. And they're very good forecasts for actually predicting load. And as I said, they control the generators the way they want it. So this is a new reality. This is a slide that I stole from them, obviously. And so you see now that one of the things that you don't have is control over all the generations. They have a lot of wind in the northwest of the state. They have also different types of generators that they control, but in the middle also they now have big data centers. Texas is building a lot of them, which requires a very significant amount of energy. They have also a lot of energy storage, which is sometimes a generator and sometimes a load, and I will talk about how to actually control them later in the presentation. And then you have the load itself, which is much more complicated because now you have houses with solar panels. You have houses with batteries, you have electrical vehicles, there is almost electrification of everything, and many of these things are becoming highly unpredictable. So even predicting load now is a very big challenge, and the interaction between transmission and distributions is also very difficult. So in other words, we live in a very complicated world, and one of the things that ERCOT believes, for instance, is that they have to investigate AI to see if that AI can actually help them manage some of these systems. And I'll come back to that. So this is what I want to convince you at the end of these three hours. And the first one is that AI is ready for some critical power systems applications. I'm not saying all of them, but for some of them, AI can make a significant difference, and I will try to convince you of that today. The second thing that I want to tell you is that potentially AI is the key enabler technology for some applications that cannot be done with traditional optimizations or control technologies. So in a sense, what I'm telling you is that AI can help, but also AI is going to be super important for some of these applications, and I don't think they would be practical otherwise. All right, so that's the two things that I want to do today. I'm only going to talk about good news, so everything which is bad news I'm not going to talk about. So you're going to have this kind of Pollyanna talks today. Everything that doesn't work, I won't tell you. Everything that we failed to do, I won't tell you. Okay, so it's a very positive talk, which is important, right? This is where we live. What you see there is the Coda building. That's where my institute is located. It's a very famous building now because we are featured in the trailer of the latest Marvel movie. So it's an iconic building inside Atlanta. If you want to see it better, this is what you see. This is before it was built, but it's really like this. And this is our data center, one of the best in the US, but nothing compared, obviously, to the big tech companies. We have another thing which used to be really nice. We used to have the largest spiral staircase in the world, but somebody beat us, so I can't even argue this anymore. But roughly speaking, it's a very interesting building. If you come to Atlanta, let me know. We can show you around. And you can see the various things that we are doing in this lab. A lot of what we do inside the AI Institute is use Inspire. We have a lot of different partners. We work very closely with them. I can't show you all of them, but these are the ones that are willing to be mentioned publicly. We also work with a variety of universities across the world and also a variety of education institutions from K-12 to, obviously, universities. So when we work with industry, we work very closely with them. We have a lot of meetings with them to understand the problems that they work on, and we try to see if AI can help them. Typically, people come to us because they have a problem that they don't know how to solve, and we try to use AI to help them. We have a big team. This is some of the people. It's not updated, but roughly speaking, we have a lot of people. They come from different backgrounds. That's what is nice. Some people have a lot of expertise in AI. Some have a lot of expertise in optimization. Some have a lot of expertise in power system. Some are in computer science. Some are in industrial and system engineering. Some are in electrical and computer engineering. So it's like a multidisciplinary team, and this is very useful when you talk about something as complex as the power grid. We love optimization. We are supposed to be an optimization group, AI and optimization, and fusing the two technologies. And we like optimization because when you have an optimization problem, you write a model, and then you get some input, you put them in an optimization solver, and then you get an output, which is typical an optimal solutions or locally optimal solutions. But this is kind of magical. It's like you give the specification, the input, and you get an output, which is what you want. There are some challenges, obviously, and one of the challenges is that optimization may be very hard and may be too slow in certain circumstances. And this happens when you have real-time constraints, which is typically the case in some application in energy system, or when you have operators in the loop. Typically, operators don't like to go and get a coffee and wait for 40 minutes. And then when you want to run very, very large Monte Carlo simulation where optimization is playing a role. And so for all these applications, optimization may be too slow, and therefore you want to do something different. But one of the things that is important is that when you live in the real world, you typically have all these optimization problems over physical infrastructures. And these physical infrastructures don't change very often. If you have a power grid, it takes many years to actually build a new transmission line or to build a new nuclear generators. If you work on the ports, you don't build a key crane every year. And if you work in a manufacturing environment, you don't build a new assembly line every day. So what is happening a lot in industry is that you keep solving the same problem over and over again with different instances, but typically they are reasonably stable, so you can predict what they're going to be. For instance, if you think about a power system, your load consumption is highly predictable in general. So it's not like the system is completely unpredictable. It's not a chaotic system. And typically, in addition to that, in addition to knowing a little bit what the distribution of instances is going to be, you also have a lot of historical data and very good, or reasonable forecast of what the future can be. So in a sense, you can predict what the kind of instances you will have to solve, and you solve the same problem over these instances over and over and over again. Okay? Everybody with me? A little bit, Okay, good. So what we are solving is what we call multi-parametric optimization problem. So you have an optimization problem which is the same for all the different instances. The instance data here is X and is going to intervene in the objective function and inside the constraints. But this is the same core optimization problems that we're going to solve over and over and over again. Okay? And we have real-time requirements. Typically, this is where the technology that I'm going to present today is important. So we have real-time requirements, which makes the optimization models, the optimization system, although they are very good, too slow in practice. but we often have a very good distribution of instance. We may predict it in a real-time manner as well. I'll tell you about that later on. But we typically learn it both from data and from physical system, and I will tell you why that is important later on. Okay, that's what we're going to do today. Okay, so in a sense, when you think about this, you can view an optimization model as a function, right? So I give it some input, some instance data, and I get some output, which is an optimal solution. So it's a function, a mapping from input to optimal solutions. And when you see that, you say, well, but this is amazing, because if this is a function, machine learning is a universal function approximator, and therefore I can use machine learning for actually approximate this optimization problem. And now instead of taking massive amount of time, I can do this in milliseconds. Okay, so one of the ways you can do that is use supervised learning. So you assume that you have some inputs, let's say the load of a power system, and you have some output, the set points of the generators. And then you choose your favorite machine learning model or architecture, which is typically parameterized with a set of parameters. We call them theta here. And then you solve an optimization problem, but you solve it offline, obviously, where you find the best parameters for your machine learning model such that you make sure that the prediction done by your machine learning model are as close as possible to the ground truth that you have. So you train this machine learning model, you train it offline, and then you can actually run it in real time very fast afterwards. Now, the loss function here should be, I want the prediction and the actual decisions to be as close as possible using some norms, for instance. Okay? So that's what we want to do. Okay? Any questions about this? No? You love it? Okay, fantastic. So you train this using stochastic gradient descent in general. You take the loss function that you see there, and then you differentiate it with respect to the parameters of the machine learning model, and you have an update set of these parameters, and you keep doing this until you converge, and you basically will have, let's say, locally optimal values for these parameters, which are giving you solutions that should be extremely close to and they can be arbitrarily close in a sense, to the value of the ground truth of your particular optimization problem. So in a sense, if I summarize, what we do is we have a multi-parametric optimization problem. We assume that we have a distribution of input and the optimal solution associated with them. We move all the computational burden offline. You will learn this offline. This is called empirical risk minimization in machine learning. And then in runtime, at inference time, what we are basically doing is using this machine learning model with the optimal parameters. We give it an instance, and we get a solution. All right? You like it? Okay, so if I do power system, this is an optimal power flow, AC optimal power flow. The input is my real active load and reactive load, and my output is the set point of the generator. So what is the active power that I'm generating, and what is my set point for voltages? So this is a particular vanilla deep learning network that you can use. You start with the load. You have some encoders, and then you predict the voltage, and you predict the active the active power of your power system. So we love to evaluate this, and the first thing that I want to talk about is a little bit about the test cases that we are using. And so one of the things that the AI Institute at Georgia Tech is doing is releasing a lot of public test cases such that you can actually train your machine learning model on some reasonable instance that resemble real life. So you can access them. We have a lot of them that we are releasing right now. And one of the things that we paid very much attention is to make sure that these are reasonable test cases. They model a real system as closely as possible. So what you see there is kind of the cosine similarity of the test case that we are generating. And one of the things that you see there is that they are not like very, very similar. There is a lot of differences between them. And you also see that we are basically scaling the load factor. So we have a scaling of the load factor, and then we have typically a lot of noise, correlated noise, when we have geographic information on the system, such that we have a very representative set of test cases. It's very important to do that because it's very easy to learn something if all the instances are the same. So what we make sure is that the instances that we are actually testing, and when I'll show you experimental results, that's what I want you to be sure of, the instances that we are generating are very diverse in spirit. You also increase typically the load in such a way that at some point you generate instances that are infeasible. You don't have enough generation or enough transmission to actually satisfy them. But sometimes you have some of these instances that are feasible and they are in that space. And these are very difficult instances in general. If you want to read about how we generate that, we have a paper that was published a few years ago. And one of the things that we are very proud is that we are actually, this is on the French system. And we are basically capturing, this is aggregate data that they release. They don't release the bus data, but you can disaggregate it and see what it gives you. But what you see is that we cover very well the various distributions for different periods in time during the year. In Europe, it used to be the case that the peaks of consumptions used to be in the winter. It's changing now with climate change. But roughly speaking, what you see is that there are different distributions, and we covered them well with the instance that you have. If you generate instances naively, you would not get that. So read that paper. It's a beautiful paper. So once again, if you wanted to get the test cases, they are available. You can actually use them. So we put the ground truth and some basic machine learning model available as well that you can use. So the question to you is that I'm talking about all this magical machine learning model that can do power systems operations. Does it work? Does it work? No? So you're basically telling me that everything that I told you is just, random, bullshit? No, it doesn't work. And why? Because machine learning is essentially a regression task. And because it's a regression, all the constraints in your power systems are going to be violated. And so even on a very simple IEEE 14 test cases, you have massive power balance violations, and you have violations of the generator constraints. And the optimality gap on something small, like 14 buses, right, is about 2%. So this is like really, really bad. Okay, so you violate the constraints, you have an optimality gap, which is very big. So, and the reason is that you have very, very significant physical and engineering constraints. So what you see at the top is basically the engineering constraints. You have the constraints on the phase angles in general, the constraints on the reactive and the active generation. You have also constraints on the thermal limits of the line. You don't want to violate them. And then you have the physics of the power system, which is typically the Ohm's law and Kirchhoff's law. And so these constraints, you have to satisfy them. But if you do a regression, they are going to be always, always, always violated. So one of the things that we did was saying, OK, so can we fix that? And one of the things that you do typically in optimization is actually using Lagrangian methods and trying to put your constraints inside the objective function and try to minimize both the object, kind of the cost of the generation, but also the violation of your constraints. And one of the approaches that you can do is to do what we call a violation-based approach. And what you do is you take every constraint and you measure how they are violated. So if these are equality, you take the absolute value. If they are inequality, you take the max of the linear, the subtraction between the right-hand side and the left-hand side. And so you put that in the objective function and you train your machine learning model with a loss function which contains both the objective function, the true objective function that you are trying to minimize, but also the violation of the constraints. And this is how your network start looking at. So you still have the encoders, but now you are predicting the voltage set point, you are predicting the phase angle, you are predicting the active and the reactive power, but you are also modeling here Ohm's law and Kirchhoff's law inside your network. And so all these things are connected to each other. And inside the objective functions, you are going to look at these guys, obviously, because you want them to be as close as possible to the ground truth. But you are also going to take the values that you compute for the Ohm's law and Kirchhoff laws and make sure that the violations are as small as possible. OK? Clear? OK. So how do you do that? You have a loss function which has these two terms. You want to be as close as possible to your set points. And then you want to minimize the violation. And you have a sum of the two things together. the key point is how do you find the right Lagrangian multipliers for these constraints? And one of the things that we did when we were doing this is using concept form optimization. We use a lot of the things that you're going to see in this talk is bringing a lot of concept form optimization into machine learning. And so here what we did was using Lagrangian duality. So in Lagrangian duality, if you have the Lagrangian multipliers for penalizing the constraints, you can assume if they are fixed, you can train your neural networks for actually minimizing that particular loss function with these fixed multipliers. And in Lagrangian duality, what you want to do is find the best multipliers, the multipliers that are going to give you the maximum value for this relaxation. And so how do you do that in practice? In practice, you basically can train the network the way I've shown you before when you have the multipliers. And then you're going to update these multipliers using a dual step. And so what you see there is that this is the training of the, what you see there is the training of the, when you know the multipliers, you get these new multipliers. Then you can compute the violation and you update the multipliers. And so the constraints that are more and more violated are going to get, more and more. The weight of the multipliers are going to go up and up for those particular constraints. Now, when you look at how it works, on many examples, it's actually reducing the violations very, very significantly. But it has no guarantee. It's still a regression. And on this very simple example, you see improvements, but you also see that there are still significant violation of the power balance and also the constraints on the generators and the optimality gap, although it typically decreases, is still there. So this is not something that you would want an operator to use because, again, you are violating the constraints. So this was nice. So this is something that we keep using, but it provides no guarantees. It's not something that any operators would be comfortable deploying in practice. So, in a sense, if I articulate the challenge here, is that what we are trying to do is not simply empirical risk minimization. It's empirical risk minimization under constraints. And the constraints that we typically have are physical constraints, our engineering constraints, our business constraints, and you need to satisfy them. They are hard constraints. And so what we want is the system to be completely reliable. So we want the models to be reliable in practice. And one of the things that I will show you also, and Spiros is going to build on top of many of the things that I'm talking about, but we also want performance guarantee. If I give you something which is actually physically valid, it also has to be somewhat close to the optimal solution. So as an optimizer, and Andreas is here, right? So somewhere. Where is Andreas? He's over there. Andreas will tell you that an optimizer wants two things. You want a good primal solution, but you also want a bound telling you how good that primal solution is if you cannot find an optimal solution. So that's typically what I teach my students. You want two things, a good primal bound, a good dual bound, and you want the gap to be as small as possible. And I'll talk about that as well. And then you want to scale. Some of the problems that we have dealt with have about a size of about 1 million of input and about 100,000 outputs. Now, think about that and contrast that to typical applications in machine learning. In machine learning, if you try to recognize an object, you have a bunch of categories. It's a very small output space. If you are looking at an LLM, it's going to be the next word or the next set of words. It's a very small output space in a sense. Here, the output space is very, very large. It's very, very different kind of machine learning problems that you're trying to solve. So that's what I'm going to talk about today. So all of what I was talking so far is just the introduction, right? So now I'm basically articulating the challenge for you. Okay? Everybody on board? Everybody pumped up? All right, good. Okay, so this is I'm super proud of this. This is an article that we actually wrote in a law journal. So I'm super proud because I have papers in law journal, I have paper in medical journals, and I have absolutely no background in those areas. But this is essentially talking to lawyers in saying, when you think about this is the consideration that we have to take into account when we want to deploy AI in something which is critical for a critical infrastructure. So most of what I'm going to do is focus on intuition today. I'm going to give you some nice mathematics, but mostly what I won't give you proofs. I want to give you as much intuition as possible so that you understand what we are doing. So there are 6 images that I want you to understand. So this is the first one, this is the second one, third one, fourth one, fifth one, and sixth one. And so at the end of these 3 hours, with some interruption, obviously, I want you to remember what these 6 pictures are, and you should be able to tell me what the intuition behind every one of these 6 pictures are, right? So that's my goal. At the end, I'll give you an image, and you have to tell me what it means. Is that fair? All right, good. First image, first thing that I want to tell you is that we're going to talk about physics and obviously electrical engineering. So the first thing that I want to talk about is this. This is differentiable programming. You're going to see what we are capable of doing with these new technologies that emerged in the last 20 years. So I'm going to talk a little bit about power system. This is a project that we did with MISO. MISO is the Mid-Continent Independent System Operator in the US. They cover everything from Canada to Louisiana. It's a very thin vertical slice of the United States. There is a lot of wind in the north, some sun obviously in the south, some congestion in between. But one of the things that MISO wanted to do when they work with us, we work with them for about 5 years, is actually seeing how we can make the system introduce more renewable energy inside the system and what are the consequences of that. So I'm going to tell you a little bit the pipeline of an independent system operator in the United States. It's different in Europe, but many of the problems are still relatively close. And I think from what I know of Canada, it's very similar, although there are differences in the time frame and things like this. So one of the big things that you have to decide in power system is which generators you commit at any point in time. So you have to decide which generators are going to generate power for every hours of the day. And then, this is typically done the day before, and then afterwards you have the dispatch problems, and the dispatch problems is how much electricity each generator is going to produce and what reserve is going to provide. The reserve are there. If something happens in the system, you can recover from the failure of another generator, or the failure of a line or something like this. I'm going to go through the various steps so that you understand them. This is the day-ahead market. It's typically, for MISO, it's typically 10:30 the day before the day of operation, and they decide based on the offers that they get from generators and load what generators are going to commit. Now, in the United States, most of the bids are actually virtual bids. There are people bidding the market. They don't have power. They don't have consumptions, but they bid such that they can sell the electricity that they get or the electricity that they will consume the next day. About 6 hours later, the MISO is going to basically look at the reliability commitment. This reliability commitment takes the forecast, the bid and the forecast, because people are not necessarily bidding truthfully in those systems. And then they are going to decide if they need to have additional generators to be committed. Every 6 hours, every 15 minutes, although they do that mostly manually, as far as I remember, they have what is called a LAC. It's a look-ahead commitment, and this look-ahead commitment is again looking for the next, next couple of hours if you have enough generation. Again, you can commit more generators there. Typically, they use a few scenarios, and they try to decide if they are in a good shape at this particular point. And then you have this beautiful real-time market where every 5 minutes you have to match consumption and generation, load and generation. And then you repeat every 5 minutes. So what I want to say there is that we have real-time constraints. So you have to make these decisions in every 5 minutes. So let me tell you a little bit about this economic dispatch that the US is running. The first constraint that you see there is the constraint that is never negotiable. It's meeting the load and the generation. So this is the power balance constraint. What you generate has to match exactly the load to a certain, with a certain, kind of degrees of freedom that the control system is going to take care of. Then you have the reserve constraints. You have to provide enough reserve. In a system like MISO, you have about 12 of them. I'm only showing you one here. But there are different types of reserve, which are dealing with different types of contingencies. But you have to provide enough generation such that you can recover from any kind of event that you are modeling. And then you have the engineering constraints. So the power that you generate plus the reserve has to be smaller than the capacity of the generators. And the reserve has some limits as well that you cannot exceed. The next constraint that you see there are soft in the United States in general. These are the transmission limit. You are basically looking if the power that you generate doesn't, is within the thermal limits of every lines. They are soft constraints, but with an amazingly large penalty, which means that in practice they are satisfied 99.99999% of the time. but they are soft constraints. I can't show you any data on the US system because this is controlled information in the US. So what I can show you is something where you imagine that MISO takes over the French system. I'm not saying that this is a good idea, right? So, but if MISO would operate, the French system the way they operate their own system, it would look like this on France. On the left, you see energy. On the right, you see the reserve. And what you see there is the economic dispatch problem. So every 5 minutes, you see what is happening, both at the energy level and at the reserve level. And what is nice about, well, I don't know if it's nice, but what you see there is that these things are changing very quickly. Partly because you have different types of generation. In the south of France, you have renewable energy, solar, wind, and so on. And you see how these things are affecting, the way you generate electricity there, and you see also how the reserves are changing. I was very surprised to see the kind of very different configuration that you get when you optimize this objective function. The big circles there that you see there are the nuclear generation. This is not the actual geography. We did actually some transformation so that you can actually not recognize where things are. But roughly speaking, geographically, they correspond to this geographic region. You see that the French people like to put a lot of nuclear generator close to Belgium, such that if there is a problem, Belgium is going to go down. So why am I talking about this? Since, obviously the MISO system works. And one of the things that people are worried about, and this is the ERCOT slide that I've shown you before, is that we have a lot more volatility and a lot more complexity in many of the systems these days. So we have obviously renewable generation, which is much less predictable, wind, solar. We have also these massive batteries that you have, that we can use, which is an asset, but it's also complicating the way we manage those systems, and I will talk about that later on. We obviously have big data centers, and then on the right, you see the complexity that you have when you are trying to predict the load. A lot of electrifications of the transportation industry, almost everything, and then the solar panels that are basically depends on the weather again and change the load of change the shape of the load. So one of the things that a lot of the operators have been asking us is to actually say, can you actually build risk assessment dashboard? I want to see what is the risk of my system at any point in time. And if you do something like that, let's say you want to do that the day before, you commit your generators, and then you say, okay, so I want to see for the next 24 hours, what is the risk in my system? And typically what you can do is very large, Monte Carlo simulation. You generate a lot of these Monte Carlo simulation based on the distribution that you have, and you run your entire system for 24 hours. That's what you would like to do. Now, you want to do that in real time as well. As I told you, the forecast is changing. Weather may change very quickly. And therefore, you want to see that, you want to do that, kind of every hour, or every 15 minutes, or every 5 minutes. That's typically what you would want. But if you do one simulation, okay, for 24 hours, you have to solve about 300 of this economic dispatch. And it would take about 15 minutes, even with the best solvers out there. So in a sense, one simulation is taking 15 minutes. If you want to run thousands of them, you can see the demand in CPU time. Even if you have a very large cluster of high-performance machine, it's still going to take you a long time. If you want to do it in 5 minutes, this is not possible. So you can't do this. So what are we going to do? So what I'm going to tell you is whether we can actually do these kinds of risk assessment in real time. That's my first goal. This is something that we could not do 3 years ago. And what I want to convince you is that we can do this now. And this is a game changer for the industry. So the first thing that I need is a crystal ball. My crystal ball is actually predicting what the load and the generation can be. And so we have to forecast, if you look at a system like MISO, we have to forecast about 10 to the 4 time series together. And so what you see there is a prediction of a lot of the scenario for the wind on the MISO system. You also see the ground truth. So this is the ground truth. Obviously, you don't know it when you are predicting. And you can see the scenarios that we are generating. Obviously, the tail there is closed, and this is like 24 hours before or something like this. What you see there is where these wind farms are located on the MISO system. And you can see when we overestimate or we underestimate the wind. The key point here is that we are actually predicting all these time series together. It's not like we are predicting them independently. We predict them all together because we want to exploit both spatial and temporal correlation, and then we want to do uncertainty quantification. So this is what we are using. We have a paper that you can read on applying some of the techniques that are in temporal fusion transformers for energy system. But roughly speaking, this is a combination of traditional LSTM technology together with attention mechanism and transformers technology. So this is these two things together. What we predict are quantiles, various quantiles for every one of the time series. So when you predict, you get these quantiles by predicting everything together, but what you predict is an independent set of quantiles for every one of the time series that you are interested in. This is a little bit going into more details. It's a complicated infrastructure, but what you see at the middle is this multi-head attention mechanism. So for instance, these kinds of temporal fusion transformers discover automatically that you have no sun during the night, that the wind is stepping up in the morning, and so on. So they basically discover all these things automatically. Now, one of the yes, sir.
How do you balance your observed inputs with your horizon? Because given your data sets,
So there are two things that we do. We have a lot of historical data. So we have massive historical data that represent the past. Okay, so that's one of the things that we use for training. We also know what happens in the last couple of hours. That's also an input of the system. And then we have also what we call future covariate. For instance, if you are in Alabama in the US, you would know that on Friday night there are high school football games, and that the load is going to increase. So we have both information from the past and information of what the future can be. We also, and I'm going to tell you that in a moment, I think, we also use physical model on the weather. So we have information of what the weather can be in the next couple of hours. So we use both data-driven. It's both a data-driven and a physics-based model, because if you don't have the weather, you would do much worse prediction. Okay. So the second thing that we are doing, I told you that we are only predicting quantiles. If you want to generate scenarios, you want to restore the correlation, spatial and temporal correlation. So how do we do this? Once again, these quantiles are very complicated. These are the distribution that we are predicting are not kind of very well behaved distribution that you would get into your probability and statistic courses. So what we do is we take them and then we basically normalize them such that we have, essentially a recasting of this empirical distribution into a normal distribution. Once you have this normal distribution, you can estimate the correlation between, the empirical correlation between different time series. Once you have this distribution, once you have this correlation, you can actually do, because this is Gaussian snow, you can generate correlated scenarios. And that's what you get here. Then you can do the reverse mapping. You map back into your original distribution, and now you have correlated scenarios. So once again, if you want all the details, they are in the paper that we wrote. But roughly speaking, what you do is you make sure that you take this independent distribution that we predicted with the temporal fusion transformers. We map them into Gaussian space. We get the correlation, the empirical correlations that we have, and then we map that back into the original distribution space. So this is one of the things that addresses your question. There is a very big difference between just pure data-driven and just weather-informed. Weather is not enough on its own, and data-driven is certainly not enough on its own. So we basically combine the past data and the weather forecast, which would be kind of the prediction on the wind, on the humidity, on the temperature, on almost everything. If you have a system like MISO, you can lose the wind in about 3 hours if the temperature is going is becoming very low. I assume you experienced that in the winter in Montreal as well. So this is what you see. You see that the scenarios are much better if they are weather-informed compared to if they are data-informed. You see that the scope of the set of scenarios is covering the ground truth in a much tighter way, and it's also making fewer mistakes compared to the purely data-driven aspect. We do also conformal prediction, although there are obviously limitations to what you can do when you do conformal prediction for temporal data, because you don't have this interchangeability property. But roughly speaking, we also try to get a sense of what are the uncertainty cone for every one of these time series. And that's what you see there. And once again, we can see that we are really, and this is load, it's easier than wind, but we are covering the load much better, and we can really talk about the uncertainty around the scenarios that we are generating. So these are more pictures. They are cute, but these are for different wind farms, different loads, and so on. And obviously, the uncertainty is going to be different for the loads and the wind and the solar farms. These are some kind of results that I want to give you. I told you that we needed a crystal ball. This is my crystal ball, essentially. This is how good I can predict the future. If you look at load, typically this is around 1%. We can predict load, even if it's a system where there is solar panels and so on, within 1% of accuracy. It may change. It may become more and more difficult in the future. This is wind. Wind, we are typically within 8%, which is not bad, right? So it's not exact, obviously, but we are still within 8%. And solar generation is about 3%. So we have a reasonable crystal ball now for actually estimating what the future can be. And so based on that, and this is also kind of measuring, I won't go into the details, everything is the paper, but what we show here is that the scenario that we have are actually capturing correlation very well compared to other methods. Again, everything in the paper that's like 40 pages long. So now I have a very good crystal ball. I know what the future can be, and the next thing that I need to do is to keep the lights on. I have to make sure that I'm reliable or trustworthy, right? And so you remember my beautiful machine learning model, which doesn't work. And so the first thing that I want to do is restore the power balance. That's the constraint which is not negotiable. And so what I'm doing is essentially generalizing the architecture of the machine learning model to actually have a new layer, which we call a repair layer. So what we get is the machine learning model is going to give you an approximation of let's say the active power and the voltage magnitude of every one of the generators. And then in this particular case, MISO is only looking at active power. And then you have a repair layer, which is going to take this approximation and generate a feasible solution. And so this architecture that we call optimization proxies are going to guarantee that you satisfy the constraints of your system. Okay, that's what we are doing. So in a sense, this is a visualization. This is 2 generators, okay? And obviously, in this particular case, linear constraints. So this is the feasible space there. And obviously, it's changing for every one of the instances. Obviously, in practice, we have to do that with 10,000 generators or 60,000 generators. So I'm just showing you something that you can visualize. And this is the value of the optimization solver, in this particular case, Gurobi. This is the value of the ML model, and this is the optimization proxy, where we take the approximation and repair it. And so there are a couple of things that you need to see here. Look at the machine learning model. It can be completely outside the feasible space. The proxy that we are building is almost always on top of the optimal solution, right? And you can see here the violations of the ML model, the violation of the proxies, which are always 0, because we guarantee feasibility. And you can see the optimality gap, which is typically very, very small. Okay, this is in percentage. Okay, so one of the things that the repair layer is doing is take this approximation by the machine learning model and then projecting back inside the feasible space. That's what we are doing. All right, so that's the point. So in a sense, what we need to do is basically train this architecture, this AI architecture. Now, this is where differentiable programming is very nice. We want to basically take this loss function, which is still the same. This is still this supervised learning problem, where I have my prediction and I have the ground truth. And I want now to basically update the parameters of my machine learning model. And so by the chain rule, you can take this thing, differentiate with these parameters, but one of the things that you will have to do is to be able to differentiate through the repair layer. And that's interesting, right? Because this repair layer is actually restoring feasibility. It's not something that is, normally, easy to do. But we have an amazing mathematician, French mathematician. Anybody knows who he is? You all know him. If you took an algebra class, a linear algebra class, which essentially everybody in this room, I'm pretty sure took, you know who this person is. So this is Cauchy. And one of the things that he did in his life is prove all kinds of theorems that seem to be completely useless, but at this point they are amazingly useful. And one of these theorems is the implicit function theorem. And what this thing is basically telling you is that you can actually get in closed form the differentiation of an optimization, the optimal solution of an optimization, the optimal solution of an optimization problem. And so I'm going to tell you what this means. So Typically, your machine learning model will have functions that are very easy, like combine a Cartesian product or a ReLU or something like that. But one of the things that this repair layer is going to be something implicit. You find a value, you find a y such that you satisfy an equation. So you can put in this repair layer the solution to a set of equations. Obviously, that solution function, you don't have a closed form for it in general. But what the implicit function theorem of Cauchy is telling you, you don't have a closed form solution for the function, but you have a closed form solution for its derivatives, for its partial derivatives, which is kind of amazing, right? This is proven in like the 18th century or the 17th century, I don't remember. And this theorem is actually super useful for us. Because what does it mean? It means that in the forward phase, when you are basically going through your architecture, you can solve a system of equation. But then when you want to back propagate, in the chain rules, you have this closed form here that you can use to back propagate and tune your parameters of your neural net. And so in a sense, this is the closed form, and it's used the Jacobian with respect to the parameters and with respect to the optimal solution that you have, the solution to the equations. And so you have this function, and you can actually back propagate through it. This is like magical, right? And this is all like 3 centuries ago or 4 centuries ago. So how do we apply this to the problem that I've mentioned? So one of the things that you can do when you want this repair layer is do a projection. You want to find the feasible solution to your system, which is as close as possible to your prediction. In general, your prediction is super good, right? So I told you, we are very close, but we violate the constraints. Can you actually find a feasible solution, project to your feasible space? And so one of the things that you can do is express that as an optimization problem. Now, by optimization theory, you know that this is going to satisfy the KKT condition, which is a system of equations. And so that's the set of equations that you want to solve. And once you have this system of equations, the optimal solution of your optimizer is going to satisfy them. And then you don't have the solution function of this system of equation, but you have a closed form for the derivatives, and you can know exactly how this optimal solution is going to vary if you change the parameters of your problem. And this is magical because now you can propagate back. All right? So that's one of the things. Yes.
So what do you do with inequalities? You assume strict complementarity?
I mean, we don't. They are in there, right? So you can solve this thing. You can, you solve an optimization problem and you have an optimal solution. As soon as I have an optimal solution, I know that it satisfies these KKT conditions, and then you just apply the implicit function theorem to these KKT conditions. You can have arbitrary constraints, and this would work, right? You see what I mean? Okay. Now, in an optimization problem, if it's nonlinear, right? If it's nonlinear, you're going to get a local optima, obviously. And so people may say, you don't get the gradient of the global optima, but nobody can get that global optima. But you will have people in optimization theory that's saying, hey, but you may have the wrong direction. But you will have the wrong direction. There is nothing else that you can do anyway. So that's one of the things that you can do. Obviously, doing this requires solving optimization problems during the training, which is consuming. But sometimes you can do better. And there is a whole theory, on what can you do what can you do in polynomial time instead of having to solve these optimization problems? And I'm going to show you that you can do this super quickly for the economic dispatch that ISOs are using in the US. And so what I'm going to do is dedicated projection layer for the economic dispatch. I'm going to show you that the repair layer can have something which restores the power balance and then can restore the reserve constraints. And so instead of having a projection like I've shown you using Cauchy's implicit function theorem, I'm going to basically use these repair layers, and I'm going to guarantee that I'm going to find a feasible solution, but I'm going to do that in polynomial time and very, very quickly. Okay? And the key idea is to take intuition from what you typically do in control theory, the control systems of the power system. So I'm going to illustrate that in 2 dimensions. Remember, we have to do that in like 10,000 dimensions or more, right? So typically what you have when you have this power balance is that you are typically violated violating it because you are not generating enough power or you are generating too much power. And so the key point is that to take these generators and then scale them up or scale them down, such that like the control system would do, during frequency, or droop control responses, such that you make them satisfy the power balance. And so what we do is a proportional response. We compute how much we have to scale the generators up and down, and we get this formula there. Okay, so I think, oops, sorry. And we get this sorry, I'm going way too fast. So we get these beautiful equations. Why are they beautiful? Can you tell me why they are beautiful? Andreas, you have to tell me why they are beautiful. They are essentially, well, they are linear and they are differentiable almost everywhere. So it's amazing, right? So I can take these things and I will be able to backpropagate through them because they are differentiable, right? So this is amazing, right? It gets me excited, even though we did that 3 years ago. But anyway, it's kind of nice. Now, for the reserve, it's much more complicated because you have to, you can't just scale everybody down. You have to know if you bump into the reserve constraints or the generation constraints. But there are two classes of generators. They are the cheaper generator. And the cheaper generator, the power system is going to try to, to basically, schedule them as much as they can. So if you want to increase the reserve, you would have to actually sacrifice some generation. That's one of the degrees of freedom that you have. And then you have the expensive generators that nobody wants, and typically they have a lot of, it's easy for them to increase the reserve, to increase the generation. So what you need to do is kind of balance these two things such that you restore the reserve. So you can decrease the generation, you can increase the reserve using these guys, but then you have to decrease the power. And these guys, they typically are the maximum for their reserve, and you can increase the generation a little bit. So you're basically trading these things off. Now, this is the algorithm to do that. Once again, I won't go into the details. They are all in the papers. But roughly speaking, this is what they do. They classify the generators, whether they are which constraints are tight for them. So there will be constraints. There will be some which are tight with respect to the generation constraints, other ones which will be tight with respect to the reserve constraints. Then you're going to see how much you can increase them. So how much reserve you can increase, how much energy you can increase, and then you basically compute a proportional response. It's more complicated than what I've shown you for restore, the power balance. But then you get this beautiful equation again. It's just the same thing as you have seen, except that the coefficients are more complicated to compute. So what you do, so the thing that I want you to understand is that when we are running this machine learning model, you are basically going through the prediction, which is your typical machine learning model, and then we are running these algorithms on the fly. That's why differentiable programming is very important, and we generate these things on the fly. And then when you backpropagate, you don't care about this algorithm because you have this beautiful function that you can differentiate backwards. Okay? So this is cool, right? Is it cool? Yeah, it's pretty cool, right? And so you can actually prove a theorem which says that essentially this is guaranteed to find a feasible solution if a feasible solution exists. If there is no feasible solution, what the system is going to do is giving you something which is as close as possible to a feasible solution. You can also say that, you can also prove that what we are doing here is still a universal function approximator, which is very nice. So this is an example, and there are many more examples like that, where you can actually have a dedicated projection layers, which is extremely efficient and completely and essentially differentiable everywhere. It has essentially subgradients everywhere. So this is my optimization proxy. I'm restoring the power balance. Then I'm basically restored the reserve layer. I restore the reserve while maintaining the power balance. This is a little bit how it looks like. You have the machine learning model. You predict this approximation. You go to the power balance. You get another approximation. You go to the reserve layers, and you have a feasible solution. And what you do, obviously, is you backpropagate this through by using the loss function with respect to that to the parameters of the object of the machine learning model. So everything that I told you at the beginning is the same here, but what I'm doing here is that I'm guaranteed to find a feasible solution at this point. Okay? So I'm reliable. Now, one of the things that is really annoying is that we have to generate a lot of training data. And this is very, 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 very time consuming. And so if you have to solve many of these optimization problems offline, it's going to take a lot of time. And so the key point is that can you avoid this? And so this is my second picture, and you can understand what this is, right? This is a beautiful robot, okay, which is actually learning on its own. Okay, so what I'm going to talk about here is self-supervised learning. And self-supervised learning means that I don't need any training data. The only thing that I will need is the input distribution. Okay, isn't that amazing? How do we do that? We do that because we are in a very, very fortunate state. We have the problems that we want to solve. And so we are solving an optimization problems, and I know the structure of that optimization problem. I know the objective function, and I know the constraints. So the key idea here is going to be, and this is an idea by Priyadanti and Zico Coulter, and something that we did as well with one of my postdocs before, is the idea that you don't need actually training data because we know the objective function. We know that we are actually looking at optimizing, we know that we are optimizing this objective function there. Okay, that's what we want to minimize. Okay? So what do we do? So we basically do self-supervised learning, meaning that the only thing that I need is a set of input, the kind of input distributions that I talked about before. I can generate sample from these distributions. And then I use my machine learning model, my optimization proxy. And then this is what I'm solving. I'm solving an optimization problem which tries to find the best parameters for my machine learning model. But what I do is that I don't optimize a loss function. I optimize directly the objective function of my optimization problem. Okay? This is super powerful, right? So obviously, my machine learning model here is, my optimization proxy, my differentiable program, is guaranteeing to give me a feasible solution. I can evaluate that feasible solution using the objective function. And what I want is actually finding the parameters of my machine learning model such that I get the best possible solution, right? So I'm feasible by design here, and then I'm tuning the parameters such that I'm as close as possible to optimality. Okay? Cool? Now, this is not the same optimization problem that you have seen before, right? So I'm not trying to solve the optimization problem. What I'm trying to solve is finding the best parameters for my machine learning model. So it's a different type of optimization. Obviously, it's non-linear, right? And so you will find a local optima for this. But this is an interesting optimization problem. So in a sense, for those, how many of you are machine learning people? Okay, how many of you are optimizers? Okay, so I'm in trouble. There are about as many optimizers that they are machine learning people. So what I wanted to tell you, and I'm still going to tell you, is that in a sense you can view these very nice synergies between machine learning and optimization. So the way we solve this machine learning problem is using optimization. And so we have a nice optimization problem that you need to solve, to actually get a nice machine learning model. So these two fields are really merging at this point, and you can see that here. I want to show you my architecture now. So this is the way I'm going to train the differentiable program. I have my objective function here. I'm guaranteed to find a feasible solution, and I'm going to back propagate through the layers my objective function through this reserve layer to the power layer, to the sigmoid layers, and then the parameters of my machine learning model. That's what I'm doing. I don't need any kind of training data. I just need to know what the distributions of my future instance is going to be. Okay? Any questions here? It's super clear? Yes. Oh, yes. So she's asking, let's go a little bit more detail on what is happening. So I have this particular objective function, okay? And I want to differentiate this objective function with respect to the parameters there, right? So these parameters. And so by the chain rule, I will have to differentiate this with respect to this, and then I will have to differentiate this with respect to this, and then I will have to differentiate this with respect to the parameters. Every one of those are differentiable everywhere, almost everywhere, and they have subgradients almost everywhere. And therefore, I can basically differentiate this particular objective function, my true objective function, with respect to p tilde, and then I can differentiate this with respect to p hat, and I can differentiate that with respect to the parameters. And so by the chain rule, is you multiply all these things, you get essentially how you need to update the parameters of your machine learning model. And you keep doing this. So once you have these new parameters, you do the forward step again. You take your input and you go through this. You get a new value for your objective function, and then you have another differentiation, backward differentiation, for actually getting the new value of your parameters. And you keep doing this until you get to a local minima. Right? So the key point here is that you differentiate this with respect to this, you differentiate this with respect to that, you differentiate this with respect to the parameters. And every one of these steps is becoming a big multiplication that gives you basically the gradient, the subgradient updates at every step. Does that make sense? Yes?
For the data X, do you need to calculate the optimal values?
No, you never. So that's the beauty. So the question here is that for the given X, do you have to know the optimal values? No, that's the point. I don't need to. Because what? Because I know how to, so this P, whatever this is, this P there, this one is feasible. And therefore I can evaluate, it's a feasible solution to my problem, and I can evaluate its value, right? And so I don't have to actually know what is the optimal value, because what I'm basically differentiating, I'm differentiating the real objective value with respect to the parameters of my machine learning model. So I'm basically tuning my machine learning model such that it gives me the best feasible solution. I mean, it's going to be a local optima because the whole thing is nonlinear, but it's basically giving me, it's basically giving me the best possible parameters of my machine learning model that will minimize the objective function of my original problem. And the key here, the reason I can do this is because I'm guaranteeing to find a feasible solution, right? Therefore, I can actually evaluate that feasible solution. Okay? Other questions here? Yes?
Do you have a method for finding initial X or derivative?
So the question is, do we have methods for finding the initial X? So sometimes what we do is we just train the machine learning model independently, and that gives me kind of a first setting for the parameters. And then we can actually start doing the repair layer in a second step, such that we generate feasible solution. So you get a good approximation there to start with, and then you start working from there. That's one of the things that you can do. But in general, if this is super fast, you don't really need to have that. Right? So the other things that is interesting, and I think you're going to like this, is that in a power system, you always have the previous solution. You have a state of the system. You know where your generators are. But this is somewhat already captured by the constraint that you have, because typically I haven't shown you that, but the limit of the generators is given by the ramping constraints of every one of the generators. So you, in a sense, you are in a state where the previous solution is typically a good approximation for starting the machine learning model. You see what I mean? Obviously, you can lose the wind and you can do all kinds of things, but you're still in a reasonably good setting point. Okay? Yes?
If you're using the objective function as a loss function and you know that, do you worry about the different scales of the objective function with very different values for different inputs? Yeah. Do you worry that instead of a loss function where it's maybe all kind of get lower, here you can have some of the systems that inherently have higher objective function, and so scaling between the different inputs can be very weird and different.
Yeah, so the question is that, the question is that the value that you have for different input can be very different because the input can be different. And yes, this is, I mean, what you are solving is really a kind of a stochastic optimization problem, right? But what you're trying to do is in a sense, what you do is you're basically trying to find a set point for these generators that can accommodate as best as possible every one of them. So from an optimization standpoint, this is not something that I worry too much about because this is a classical, stochastic optimization problem. You're going to find the set points of the generator that are as good as possible for all the scenarios that you have. So in a sense, what you are doing is an expected, you are minimizing unexpected values. And obviously, we do that with mini batches, right? So this is not one step at a time. You have mini batches that you optimize. And so this is kind of amortized, in that particular way. In some of the things that I'm putting a lot of things under the rug when I'm presenting here because I'm giving you the intuition. But one of the things that we can do here is also very, very interesting is that you don't need to have the set of instances fixed at the beginning. You can generate them on the fly. And this is actually pretty nice because you can say, oh, I'm going to generate these instances. And then the next time around, for the next mini batch, I'm generating the instant from my empirical distribution automatically. So you don't have to have a fixed set of instances either, right? So that's another very nice thing that we have. We just need to be able to sample an empirical distribution. So I want to show you the result. First, if you look at the result on the very simple test cases that I've shown you, we have we basically satisfy all the constraints. So 10 minus 8 is like the limits of the floating point system. And then you can see that we are essentially 10 minus 6 difference with respect to the objective function, so we are near optimal. Obviously, this is IEEE 14. This is super easy. This is the kind of inference time that we take. So this is the self-supervised learning. This is the supervised learning. It takes about 10 milliseconds for a system with 30,000 buses. Or, this is the French system. This is 10 milliseconds on the French system. That's when you have at inference time. At inference time, you are extremely, extremely, extremely fast. Okay? This is the training time, and this is really important as well. I'll come back to that. We can train these systems, the self-supervised learning, in about 30 minutes for the largest system that we have there, 30,000 buses, which almost don't exist. It's 45 minutes. That gives you the time for training this. So if MISO is in a situation where they say, wow, it's getting really cold, you can retrain the model and take that into account immediately. And I'm going to talk about that in a moment. So this is very, very fast for training. So training takes about 30 minutes. Okay? And this is the kind of the value of the objective function at the end. And you can see that for most of the system, we are about 0.5% of optimality, except on this very annoying French system, because the French system is the most engineered system in the world. They have a lot of phase shifter, condensers and things like that. And so it's much more difficult to actually predict than other systems. So we have near optimal solution. So you remember that the motivation that I had is to have this real-time risk assessment, right? And we want to run that every 5 minutes. And it takes, just for one scenario, it takes 15 minutes using the best optimizers out there. So what am I going to do? I'm going to take my optimization proxies, and I'm going to replace every one of these optimization models by this optimization proxy. Now, these optimization proxies take 10 milliseconds. So I'm moving from 15 minutes to 5 seconds. So it's a game changer. So now I can actually have a real-time estimations of my system in real time. And so look at this. This is a kind of a visualization of the Gurobi solution and the solution using the proxies. And if you see differences, you have very, very good eyes, because essentially these are the same solutions all the time. I want to show you something else here, which is really interesting. So these are very different systems here that you see. This is a system which is basically a basic Lagrangian dual for solving this. This is DC3, which was a really big step in the field, but they still violate some constraints. They cannot guarantee the constraints, and you can see that sometimes they have very significant violations. This is Loop. This is a system that can guarantee feasible solution, but they are really, really bad in terms of the quality of the solutions. They have optimality gap that are massive there. And then this is the proxies that I've shown you, gap of 0% and no violation. So this is really, really what you can the kind of system that we can build. We typically use risk metrics. This is what people in in the risk analysis community want. They want conditional value at risk. They want the probability of risk of an adverse event. They also want the risk of an adverse event. And I'm going to show you some picture here of different systems. Obviously, if you use Gurobi, you have no violations of the power balance. This is the power balance. If you use the proxy, you have no violations of that. This is kind of the violations that you get from the other system. Very, very significant violations. So you really need to take into account the constraints very well. Otherwise, what you are predicting is massive violations of your constraints. On the right, this is very interesting. This is one of the things that people worried. Are you overloading the lines? And when are you overloading the lines? And so, again, you see Gurobi, the black line. Then you see the various other systems. And one of the things that you see is that many of the other systems, compared to what we do, have false alarms, which basically means that they're predicting, kind of overload of the lines at many different points where they are not. We only predict, this is us there in whatever that color is. I'm colorblind, so I don't see any of this. But this line that you see there is what we are predicting. We are always predicting violation of the terminal limit when they are, no false flags, but we are overestimating the risk a little bit. So that's, that's because we lose a little bit every time, right? So we don't have the optimal solution all the time. And so we are basically losing a little bit there. But, this is fine. I mean, we are identifying there is a risk. We overestimate the risk a little bit. This is the probability of an adverse event. Again, the big difference between the prior work and what we are doing is that we are basically we never predict violation of the power balance, obviously, and we only predict events at the right place. So that's nice. And then this is the financial risk. Again, we may overestimate a little bit the financial risk, but only when there is a financial risk. And this is kind of the total cost and how good we are in estimating the total cost of the system. So this is, I want to show you this for something which is a little bit bigger. So this is what Gurobi does, and this is what we do, okay, with the proxy. If you see the difference of the estimation, you have good eyes again. There is a difference. We actually overestimate the risk here of this particular line, but we identify all the lines where there is a risk. Okay, cute, right? I want to talk about something that every time, I presented some of the things that you have seen, people would tell me, oh, but can you actually deal with different commitments and different topologies? Because things are changing. And so the French operators, for instance, is very keen on changing the topologies and so on. And they always ask me, oh, but you assume that you have a fixed topology for your network. And so I want to give you an answer to that question. There are multiple answers, but I want to give you one. And so I'm going to give you a kind of the reality in the field when you are actually looking at real systems. So what you see on this picture is the different commitments, the number of, what is the measure there? Yeah, the unique hourly commitments of the generators at different times of the year. And so there are obviously potentially 24 different commitments because you commit the generator for every hour currently in the MISO system. And you can see that in January, most of the time, for most of the points in the day, you have different committed generators. So it's very different. So the question that they ask is actually an amazing question. It's like you are assuming that you have fixed commitment or fixed topologies, but these things are changing, right? So that's the bad news. The bad news is that everything I told you may not be valid. Right? But there is a good news as well, is that most of the time, 40% of the generators are fixed at the maximum or the minimum value. Why? Because you're always going to do the same thing. You're going to dispatch the generators that are cheap, and you want to not dispatch the generation that are expensive, and you only dispatch them when there is congestion in your system, or voltage issues and so on. So there are these two things that are interesting. So this is kind of the input of a model. The model is typically very large because you take all these things and they are proportional to the number of generators, proportional to the number of buses. And that's why you have this very large input space that I was talking about. But one of the answers to the question that people ask me when you have different topologies and so on is that, well, we are in an amazing situation where we can do just-in-time learning. Because for us, we can generate different machine learning models for every one of the hours of the next day. And so in a sense, this is something that is really different from what typical people are trying to do in machine learning, right? So in machine learning, people will say, I want a model which is general. It applies to everything. I want foundational models. I want large language models. What we want here is small models, and they are going to be dedicated to every hours of the day, because we know what these hours are going to be the day before, and we can train dedicated machine learning model. So what you see, this is the methodology that we have. The day before, we generate data. The way I told you, for every hours of the next day, using weather forecasts and everything else. And then we basically generate a machine learning model for every hours of the next day for every one of the commitments that we have decided the day before. And so this is kind of amazing. And then what we do is we do an architecture which is a classify and then predict. We predict, we classify the generators before, which generators are at the upper bound or lower bound. We predict that as well, which decrease the size of the machine learning model that we need to train. And that machine learning model will have some binary indicators for whether a generator is committed or not. And so let me show you the results. So this is the quality of the learning model. So the model that you see is trained for every hour. This is a model for trained every 2 hours, 4 hours, 6 hours, up to 24 hours. And what you see is that the small models are obviously better in the time that we have to train them than the model that try to be general. But this is not the most important point. The most important point is this. This is the time that it takes to train models for 1 hour, 2 hours, 3 hours, 24 hours. And when you look at the time that it takes for training models for 24 hours, they essentially take 24 hours. And so using the best GPUs that were available for us at that particular point in time. So, and the other models take a fraction of the time. So we not only are super fast, but if you're trying to have a model that is very general, it's going to take a lot more time to actually train such that you have the accuracy that I've shown you on the previous slide. So in this particular case, this is kind of interesting. When you do AI for engineering, you may not want to have the most general model. Obviously, we'd like to have them, but this may be more effective to actually have dedicated model for the things that you are trying to solve. And so that's one of the answers. If the topology change, again, you're not going to open, breakers and connectors very often in a system, and it takes some time to do that. Once again, if that happens, you can retrain the machine learning model and take that new topologies. That's what I'm telling you. And so this just-in-time methodology is something that you can do in these kinds of AI for engineering problems. Okay, now I have a detour. Yeah. This is people are always asking me, oh yeah, but you are using machine learning. We are going to need some, incredible, huge data center with, 500,000, NVIDIA processor. And this is not the case. We need good machines, but we don't need a massive data center to actually train the model. We can actually have a machine which is like, $25,000 up to $300,000. And so that's the kind of machine that we need. We don't need something that costs billions of dollars to train the machine learning models that I've shown you. So, everybody with me so far? Now I'm going to show you something which is super cool. Okay? So I told you that we need two things when we are an optimizer. We need a good primal solution, but we also need some performance guarantees. So far, the only guarantees that I give you is a guarantee which is like, I give you a feasible solution, and in expectation, I've shown you, using empirical results, that is pretty good. But can you actually find, in real time, a performance guarantee for your model? So, and this is the second picture that you need to remember. And this is the mathematician which is responsible for the techniques that I'm going to use. You know him, right? Come on. Everybody should know him. It's like the most amazing mathematician in computer science of all time. So this is John von Neumann. And as you know, John von Neumann invented duality theory in a sense. And so using game theory and things like this. So what I want is a guarantee in real time on how good my machine learning model solution is, my differentiable program solution is. And so this is very important because in practice, in markets, typically you have requirements that your solution is within 1% or within 0.5%. So you need to be able to assess that. And so what I'm going to show you is so when people say, oh, you want to use machine learning and having guarantees, this is like impossible, right? But we live in the real world. And I love living in the real world because it makes my optimization problems much simpler. Okay? And one of the things that we have in the real world is that we have these beautiful constraints, bound constraints on everything. So if I'm a generator, I have bound constraints on my generation, bound constraints on my voltages. And this is amazing. Why? Because on these bound constraints, if you take the dual of this problem, these dual variables on the bound constraints are free. And you don't have a lot of free things in life, right? But one of them are dual variables on the bound constraints. And that gives me something that is very unique because I can restore feasibility in the dual space extremely easily. So what do I have to do? If I want to do a proxy for the dual problem, I can predict the y variables, which are constraints and are really annoying. Okay? But then I can restore feasibility using the dual variables of my bound constraints. And so so what I'm telling you is something which is really deep, right? If you have bound constraints on your problem, having a dual proxy is amazingly simple compared to having a primal proxy. So solutions to the duals are always much easier than solution to the primal. Okay? If you have this bound constraint. So I'm giving you another type of proxies that we call dual optimization proxies. And what you do is we use our beautiful machine learning model for actually getting a partial dual solution, not a full dual solution. And then my repair layer is basically a completion layer. I'm using the degrees of freedom that I have on my dual variables for the bound constraints, and I'm restoring a dual feasible solution. And by definition, that dual feasible solution is giving me a bound on the optimal value of the optimization problems that I had before. Isn't this cool? Super cool, right? So I have the performance guarantee. Actually, you can show that you can restore these things optimally. In this particular case, this is a linear program. You can show that you can restore them optimally. And then the amazing thing is the quality of these things. Obviously, I'm showing you on a linear program. This is the kind of quality that we have. And even on the French system, we are way below 1% optimality when you are trying to restore feasibility of the dual, finding dual feasible solutions. These are the kind of things, if you use other methods, you are typically very far away. And we are very, very close to optimality in this particular case. Now you're going to tell me, yeah, but what do you do if you have a nonlinear problem? And we go back to ACOPF. And what do you typically do when you want a performance guarantee? When you want to use a kind of a guarantee on the optimal solution of a nonlinear problem, you typically take a relaxation. And what I'm going to show you is dual relaxation proxies. So if you have a nonlinear problem like the OPF, you can take a relaxation of that problem. And these relaxations are generally very good. You can take second-order cone or semi-definite programming. And then you take the dual of this, let's say the dual of the second-order cone, and then you are predicting this dual using deep learning, and then you are restoring feasibility using the freedom of the bound variables, and so using differentiable programming. So what I'm telling you here is that I have a very systematic methodology for finding performance guarantees in real time for essentially any problem for which you have a really good convex relaxation. You take the convex relaxation, you use the dual variables of the bounds, and then you restore feasibility. And so this is super cute. Okay? So I'm going to show you that for second-order cone because this is interesting. Most of the complexity, this is in complex notation, but most of the complexity in AC power flow comes from the multiplication of the voltages. You typically, what the relaxation are doing is replacing those by variables. You lose the connection between them, but then you have some constraint to restore this connection. And those constraints, so this is all linear, so this is easy. And so this is the second-order cone relaxation. You transform the inequality in a rotated second-order cone constraints. And so this is convex. This is nice. You can actually compute this very quickly with some really good convex optimization software. So when you find, so this is getting a little bit more complicated, and I'm not going to go into the detail. But once again, I want to give you the intuition here. So when you see something like that, this is the dual of the second-order cone relaxation, but this time using real numbers. You see the dual variables there. And what I'm going to do is playing the same trick that I've shown you. I'm going to predict some of them, and then I'm going to restore feasibility of other ones. So this is the one that I'm going to predict, and I'm going to restore feasibility using the other ones. And so I'm going to show you an animation of what the system is actually doing. I'm predicting these guys completely. Machine learning, yes?
How do you choose which ones you predict and which ones you use to restore feasibility afterwards?
Yes, so the question is, how do you choose the variable to predict and the one that are going to be free? And the answer to that is that this is the secret sauce. And I'm going to show you, some results afterwards. But there are many different choices that you have here. Yeah, it's not only which variables you predict and which variable you don't predict. This is also how you represent the problem. Is it what is the convex? What is the representation that you are using? Are you in polar notation? Are you in hybrid notation? Are you in a rectangular notation, and so on? And there is a big impact of these things. So there's still very much an art in actually choosing these things, but this is a good question. But what I'm showing you, I told you, I'm only showing you the good news, not all the sweat that tens of thousands of PhD students had to go through to do this, right? So I'm exaggerating here, obviously. But this is what we predict, and you're going to see something. It's also driven by the theory of optimization, right? So when you predict these things, obviously there are some variables which are unique. You can actually predict them. Then you fill them in at different places. Then once you fill these things, other ones are filled in. And then what is nice is that you know that the optimal solution is to satisfy some properties, right? So the optimal solution of an optimization problems have always some kind of properties, complementary properties that they have to do. So when you see there are two variables which are free, but you know that in an optimal solution one is 0 and the other one is some positive value. And so using that theorem, you can actually, even though there are two free variables, you can restore feasibility because of these optimality conditions. And you do that for this one, then you have the optimality condition on the second order cone constraints, and you restore using these particular values. And then you have another one, which is, I don't remember what it is, but again, this is a second order cone coming from the optimality condition of the second order cone constraints, and then you restore the feasibility of everything. Okay? So I'm going to show you in general how you do this, but this is like what we did for the second order cone relaxation. And so in a sense, what we do is that we take these variables there, we predict them, and then you have these variables there that for which you can do a differentiable program again for restoring the feasibility. And you train this again using self-supervised learning because we have the objective function that we are minimizing. Right? So this is exactly the same thing, except that the repair layer becomes a completion layer. Obviously, there are computations that you do there, and that's why differentiable programming is good, and that's why we like PyTorch and not some of the other tools, right? Because we have this flexibility of running complicated programs when we are doing the forward pass. These are some of the size of the problems for which we have applied this. And this is answering your question, right? So you see various things, polar, rectangular, predicting this, predicting that instead. So we did a lot of experiment to do that. This is obviously predicting those and using polar notation is actually giving you the best results. You can see that sometimes we are below 0.5% of guarantees on this big system there, which is based on, again, the French system that we really dislike. It's the most complicated one. We are a little bit higher. But that still gives you some really good performance guarantees. If you look at what is happening when you are actually comparing the running time using a particular optimization solver, we take milliseconds. This is Mosaic, but Mosaic don't really have guarantees. They don't give you a dual feasible solution. They may violate constraints. So you will have to do the same kind of restoration of feasibility that we have. So which is also interesting because the things that I'm showing you can actually be used inside optimization solver to guarantee feasible solution, which sometimes they don't do. And this is Clarabelle, which is guaranteed to find feasible solution by design. But look, they take 3 or 4 or 5 orders of magnitude more for actually getting these guarantees. So we get these guarantees in milliseconds. They are very precise. And if you try to do that in real time with any system that has the same guarantees, it would take a lot more time. So this is kind of amazing. I give you a primal feasible solution, and I give you a dual bond. And so now you know how good you are in real time. So in real time, the operator can see your solution and the guarantees. And if they see this is not good enough, they could actually fall back to an optimizer if they want to. You can generalize that to conic dual proxies. And this is a bit more complicated, but roughly speaking, what you do is that you use your machine learning model to predict something. Then you have to project it in the cone. And once again, for different types of cones, you will have different projection operations. Some are more easy than others. And then afterwards, you do the dual completion using kind of the Lagrangian dual bond, which is giving you the best way of restoring feasibility at that point. And so this is NeurIPS papers that we did a few years, last year. And that gives you kind of a systematic way for different types of cones for actually getting dual proxies. So in a sense, we have a very nice theory of actually doing dual proxies using these different projections and completion layers. And so this allows us to do this thing in real time. Now, if you want to do that for semi-definite programming, it's a big challenge. It's actually very interesting because you have to start thinking about the eigenvalues and things like that. It's very difficult to do that effectively. And so I have a student spending his life doing that. So yeah, he's a very good student, but he has a very tough task. So this is the two main messages that I wanted to tell you here on the primal and dual proxies. We're going to go to more complicated things in a moment. But I also want to talk about scalability. I told you that the dimension of the output here is gigantic compared to what you typically do in machine learning, right? So you have like 67,000 outputs that you need to predict. But again, we live in the real world. And if you look at if you do a PCA analysis of these outputs, a lot of them are going to be correlated in some fashion. And so this is the difference between a computer vision system and the output, the correlation between the PCA, on that one and the PCA on what we have in power system. And you have we have much more structure, in a sense, in power system. It's a much more structured system. So one of the things that we thought about is that instead of actually predicting in the real set of output, we can actually learn in a subset of the principal component. And so what we do is that we have a transformation to actually predict a subset of to predict only the principal component. And then we have another transformation there to restore in the original space. So you have something here which is really the learning inside the space of the principal component. And afterwards, you have this linear transformation to get back to the original space. And so what you need to do is now train something like that, where we actually do online, during the training, the PCA transformation and the learning over the PCA transformation. And so what you do is that Z is going to be a subset of the principal component. These are the important things that you want to predict. Obviously, you don't know them in advance, so you have to compute. The only thing that we assume is that we fix the number of them that we want to learn about. So you learn about this set of principal components, and then you map them in the original space. That's your neural net. And so we call that compact learning. And the way you do that is by, in a sense, during the training loop, we are actually computing this PCA automatically. And there is something which is called the generalized Hebbian algorithm, which is amazing. At every step, it's recomputing the principal component and the matrix W that you see there. And then we do the learning based on that one, and we keep iterating these two steps. So in a sense, we compute the W, and then we learn inside that thing, and then we recompute the W. You do the training of the machine learning model, and we do these two steps. And the basic advantage here is that we can learn models which are way, way, way smaller. Again, all this is in a paper in the Traction on Power Systems. But roughly speaking, what you get is a much, much smaller models that you need to do. So this is like the model that I've shown you before. If we don't do anything, they have, essentially as soon as you get to 3,000 buses, we have like 200 million parameters. If you continue, you get to billions and trillions of parameters. And by doing this compact learning, we still get models which have a lot less number of parameters because, as I told you, there are a lot of correlations inside those systems. If two generators or two wind farms are close to each other, they are highly correlated, and you can actually learn the principal components instead of learning the actual wind production in every one of those. So, yes? You lose something, right? So you lose a little bit, but you lose very little. I think I have some results here. Yeah, you can see that. So I think you'll see the variance there, right? So you see some of the things that we lose there. This is the variance on the optimality gap. And so I think it's 99.95% that you get by using a reasonable number of principal components. Obviously, you can use many more, but if you use a very small number that I showed you, you are like 99.5%. That's what you have. You capture 99.5%. Yeah, and once again, this is because these things are very, very important. Yeah? And so as you see there, this is the optimality gap that you get. It's very, very small, except on this annoying French system again. But the valuations here, this is AC, so there are some valuations at the end, but they are very, very small. You can see that even the system here is actually better than the large one when you do compact learning, because you have more time to train using the reasoning train. This is a small system that we, by definition, we keep the network very small. And what you see there is that the loss that you have are significant. So the small system on their own are not sufficient. But if you do the principal component analysis and you learn on the subset of the components, you have very high accuracy. So I think this is the combination of having a small model but learning in the PCA space instead of learning inside the original output space. So very, very interesting observation there. And once again, this all depends on the correlations that you have inside a power system. So again, a lot of what I'm telling you is that what is nice about engineering problems is that there are problems on the real world, and there is a lot of structure because they have to satisfy physics and engineering constraints. Yes?
It seems like you violated the constraints less often as well. Yeah. So why is that?
So the question is, why do you violate the constraint less? I think the key point is that the models are smaller, you can train them better. And yeah, I think it's just that the model is much more compact and you can train them. It's much easier to train them well, in a sense, because you train them in a much smaller space and you can tune them nicely on that particular space. But once again, I mean, understanding exactly what is happening in an ACOPF is very difficult, right? So you have to recognize that there is some magic. When I talk to my students, I'm telling them, we play a lot of magic tricks here. This is one of the magic tricks that we don't completely understand. But I think the question of the variance and your questions are very good, because we capture, with very few principal components, we capture a lot of the structure of the system. That's the key point here. And this is because of the physics and the engineering constraint that you have in these systems. Now, I'm going to show you something which is truly beautiful. This is the most amazing thing. So one of the things that I wanted to convince you is that we can do now things that you're going to do before. And this is one of them. Can AI deal with contingencies? When we talk to ERCOT, they don't only do n-1. They want to do n-10 or n-15, because there are various scenarios where they lose the wind there or there is massive congestion there. Much more than what typically happens in power system, because the system is much more difficult to manage these days. And so this is a painting. You'll have to remember there. This is one of my favorite painters. He's Belgian. And so he has this beautiful, I don't know if he knows about duality theory, but he has a lot of dual pictures. And so this is what I want to talk about. So if you, in the European, I mean, in most systems, if you lose the nuclear generators, one of the things that happens is two things. The first thing is that you have to stabilize the frequency. And so this is the first thing that you have to do, and you have to do a proportional response of the generators. And then you have to, and as a secondary control, you have to do AGC to restore the frequency at the right level. These two things are proportional response of the generators. They are different, but it's always a proportional response. But when you do proportional responses, there are limitations of what you can do for the generators. I want to give you some intuition here for those who don't know power system. But these are my 3 generators in the energy that are producing in megawatt. And these are my reserve, and different generators have different reserve. But what I want to do is proportional response in terms of, for every one of the generators. So I'm sending a unique signal to everyone, and I say, please step up proportionally. And so the first thing that you're going to see is that I'm going to get 6 megawatt from everyone, because everyone can give me 2 megawatts. But no, one of these generators, this guy here, is at the top. That generators cannot do anything. So we have to adjust the proportional response to the next 2. And so we give 4 new megawatts there, and then the last megawatt is from these generators. That's what is happening. That's the way proportional response works. And so this is nasty. Why is it nasty? Because it's nonlinear. So, oops, gosh. Yeah. So one of the things that you have is that every one of the generator, for every one of the scenario that can happen, will have to step up. This is the reserve that you're going to procure. Then you have limits on these reserves. You cannot go above a certain level. But then you have this proportional response. And so this proportional response is going to depend on 2 things, the participation factor. Different generators may have different participation factor. But most importantly, you have the proportional response. So you have this unique signal for everyone. And that unique signal is going to tell, step up by that much percentage of your thing. But this is a global signal for everyone. And so when you look at that, that basically means that inside your optimization problems, this becomes a min of 2 things, non-convex, annoying, very annoying. But this is the way the real system model. If you don't capture that in your optimization model, you're not really modeling what the response of the generators are. So when you look at the security constraint OPF, that's how it looks like. So this is like the MISO system that I've shown you, but now you have many contingencies, and this is how the optimization problem looks like. That's the power balance that I've shown you, but no, and you have the thermal limit, but now for every one of the contingencies you have this, and you have this nonlinearity that I've shown you. So you repeat all the constraints, but then you also have these nonlinear constraints on how they're going to respond with this global signal. So it's a massively ugly optimization problem. I mean, no, it's beautiful, right? So, but it's ugly to solve. And so we wrote a paper like in 2021. I mean, it was published there. We took 2 years to generate it. But this is the way we can actually solve this problem using optimization. So you basically start with nothing, the nominal case, and then you add the contingencies as you discover them. So it's a column and constraint generation. You add new constraints, you add new variables, and but you need to find this global signal. And so finding this global signal is difficult. So what we do, because you have to satisfy the power balance in every one of the contingencies, and what we do is actually to do this effectively, we have a binary search algorithm which essentially says, okay, if my signal is this, what is happening? Some generators are going to be at the limit, some of them can continue, and so and you keep doing this binary search essentially for finding the right global signal. And when you have the right control signals, you will have the set points of the generator. So we don't solve an optimization problem. We identify the contingencies, and then we have this beautiful binary search for finding the global signal. We put these contingencies with the nominal case. We resolve. We identify new contingencies. We find the global signal, and we continue doing that. And so now we have to do machine learning. How many people know this person? Okay, the real optimizer know. Stephen Wright. And Stephen Wright, when he gave a tutorial at NeurIPS a few years back, and one of the things that he was telling, mostly the optimizer, right? So not the machine learning people, but one of the things that he was saying is that, well, maybe it's time to look at different methods when we do optimization for machine learning. And this is what I'm going to tell you. I'm going to talk about a method that almost nobody uses these days, which comes from this amazing person. Who knows who he is? You have to know who he is. So again, a very old, a distinguished French mathematician from a long time ago. This is Lagrange. And so one of the very old techniques that we use in optimization is called augmented Lagrangian method. And roughly speaking, if you have an optimization problem like that, what you do is you put the Lagrangian multipliers for the constraints, but then you have also a violation terms which penalize, it's typically a quadratic terms, which penalize the violations of the constraints. So this actually penalizes in both directions, whether you violate or over-satisfied. Right? And so you solve this sequence, this unconstrained optimization problem, and then you have another dual step for restoring, and you keep doing that. Solving unconstrained optimization problem, which is easy, and then, well, when I say easy, it's always relatively easy, right? So it's easy, and then you do the dual step, and you keep doing that, and you are guaranteed to find the optimal solution local optimal solution when you converge, right? So this is nice. Now, what we are going to do, I'm going to do that in the machine learning context. I'm going to do a self-supervised primal dual learning. So I'm going to learn two networks. One network is going to be the primal network, and that's the network that actually learning to solve this unconstrained optimization problem. And then I will learn a dual network, which is predicting my duals. Okay? And why is it nice? Because when I solve this problem here, I have to guess these guys. Okay, I have to guess the multiplier. I'm guessing the multiplier using my dual network. I solve the problem, and then I update the dual multipliers, which means I retrain my dual network. Yes, sir?
When you're doing this dual iteration with the self-gradient calculations, to recover the primal solution, you need a zero duality gap.
So you don't optimization problem?
Yeah.
And you have the best person to answer that question. So it's guaranteed to converge, and it's guaranteed to give you a solution which is going to satisfy the KKT conditions, right? So that's what the augmented Lagrangian method satisfies that. So, but you have Andreas next to you. He can tell you everything about this, right? So I'm assuming that this is true, right? Yeah. So, but what I'm going to do is that I'm going to use a primal network to learn this unconstrained optimization and use a dual network to learn the duals. So this is what I'm learning in the primal network. I'm learning this, assuming that I'm given this particular Lagrangian method and the rho coefficient, which is typically a constant for the violation term. And then what I'm doing for learning the dual is that the dual step is actually predicting what the dual should be. So at every time, I know what the dual should be, and therefore I can actually learn how they should be. And my dual network is going to learn this. Now, for those of you who have done Q learning, it's a little bit the same thing when you do Q learning. You learn, this is kind of the Q learning step that you can do at every stages. So you basically know what the dual should be, and you train the dual network to learn this. Okay? And so, no, this is my differentiable program. It's a scary stuff. I have the fully connected network there to and repair layers. Well, not repair layers. So for predicting my base case, my nominal case, then I restore the power balance the way I've shown you. I get my nominal dispatch. Then I do inside my training loop, I do the binary search that I've shown you before to actually connect, find the generator of every one of the contingencies, and then I'm estimating the slacks of the variables, which are basically penalized in my primal dual. And so this is how I train this thing, right? So this thing is scary to train. It's big. It's a differentiable program, which is restoring powers, the feasibility constraints on the primal, and then going to this binary search for finding the generations of the new dispatch for every one of the contingencies, and then estimating the violation of the constraints, which are basically in my primal network. So the binary search is, again, the very similar things that you have shown before. There was a basic difference compared to that, which I don't remember. Yeah, you are not completely sure. Actually, yeah, that's interesting. You are not completely sure that you will be able to restore the feasibility of all constraints, and that's why we are using a primal dual, because you are, in a sense, you are in a position where there may not be any kind of dual signals there. But the primal dual method is taking care of that. So I want to show you the result, because those results are amazing. This is kind of the size of the network. Again, big networks. This is the number of variables that you have in the optimization problems, 500,000 variables. This is the time that it takes for actually solving this problem using the best method out there, the column and constraint generation. So it takes over 2.5 hours to solve this problem to a reasonable accuracy in terms of optimality. Now, I have to solve that in the next 5 minutes, right? So, and I'm taking 2.5 hours to solve this problem, okay? If I use, so the optimization take 2.5 methods. This is the training time of my network, about 3 hours for the French system. Again, the French system is the most difficult one for us. And this is the inference time, 10 milliseconds. So in this particular case, I can solve a problem in milliseconds. It would have taken me 2.5 hours. And this is the optimality gap, typically within 1%. But again, before we couldn't do anything like this. And then my optimality gap is below 1%, and I can do that in real time. So this is kind of amazing, right? Come on, you have to tell me, yes, good work, right? OK, good job. It just only took us 5 years to do this, but anyway. Now, I want to tell you one of the things that I really like here, which is a very, very, very new work. And I want to talk a little bit back. I'm going to go back to ACOPF, which essentially nobody does really in the system. And I'm going to talk about this mathematician that you probably don't know. I had no idea who he was. He's a Russian mathematician, which is called Sobolev. Okay? And so one of the things that you have when you try to apply many of these techniques on ACOPF is that you have this curse of outliers. There will be outliers, and these outliers we don't do a very good job on. And the reason we do that is that so far we are learning functions which have no constraints. We are learning any functions. And once again, we ignore a lot of the structure of the problem, right? So what I want to show you is that we are actually going to learn in Sobolev space. And what is Sobolev space is that we are actually specifying not only what the function should have as optimal value, but also we are basically saying you have to satisfy the partial derivative of the actual function. So imagine in supervised learning, we will not only give the optimal solution that we want to approximate, but we also would give the partial derivatives of that particular solution. And we want the function to be good with respect to not only the solution that we are computing, but also the partial derivatives. So you are actually putting a lot more structure on the functions that you are going to learn using the machine learning model. And so this is essentially what you are doing. You are basically saying, hey, I want my loss function or my self-supervised loss, but I also want to be sure that for a sample of the partial derivative, I'm going to be very close to them. And so I'm restricting the space of functions that I'm actually learning. And so when you do something like this, what is nice is that if you assume that your functions or your partial derivatives have some Lifshitz continuity properties, which they have when you do ACOPF, you get some very nice theoretical guarantees. And so these theoretical guarantees are going to tell you how far you can be from the optimal solution. And so this is kind of super amazing, because now we are in a space where if you restrict the space of the function, you get these guarantees. I'm not saying that they are very tight, but you have formal guarantees that you cannot be. If you are in a very small region, you will have the guarantees. And therefore, you can train, using this subset of inside the Sobolev space, which is actually smaller than the original space we were looking for. And so one of the big things is that when you do that, you don't really improve the expected case, but what you really do better is dealing with all these outliers that you have sometimes. So these machine learning models are going to be super good in expectation, because that's really what you are doing. But there will be outliers for which you can have a loss of 10% or 15%. And what you see here is that we are basically eliminating all these outliers by using this Sobolev training. And so this is very interesting. By using these additional properties, we get the same quality of solution, but we remove the worst case in a very significant fashion. And that's orders of magnitude better. And this is one of the things which is really nice. So when you think about these machine learning models, when you have engineering application, the message here that I've been giving you in the last 2 and 15 minutes hours is really, exploit all the structures that you have, because this gives you a way to actually get performance guarantee and removing outliers. Okay, yes?
So why does mentioning the function group just help with the outliers?
I think that I don't know why they remove the outliers, right? So this is still magical in some fashion. But the point is that you learn functions that are much more reasonable. You see what I mean? And so you have restricted the power of the function that you are learning. It's a subset of the function. And by that, somehow, the outliers have been eliminated. And the reason, theoretically, what does that mean? Because we learn in that space, it basically means that if you take a ball around a point, you are guaranteed to be very good in that ball. And so in a sense, we have these theoretical guarantees. Even if the ball is large, you cannot be that bad. So, you have theoretical, the reason you have this is that you have the theoretical guarantees of the lift-shift continuity, and in the worst case, you cannot be that bad, right? So you see what I mean? No, it depends on what that radius is, right? So, but once again, if you can always say, I'm going to look at you can always do what I have done before to an extreme, which is like specializing the model to different regions of the space, right? So you can always do that, and you would be very good. Yes.
In those really well-defined problems, where could the outliers come from?
I think it's just the training is not good for those, because so the question is that where are these outliers coming from? These are not outliers in terms of the input distribution. It's outliers in the sense that we don't have the performance guarantee of the other ones. And the reason for that is that this is where typically the nonlinearity is kicking in and you don't notice it, right? So this is these points where you have the nonlinear constraints that are really important. And in that space, the regression is not good. And so I think the key point is that if you put at that particular point the properties of the derivatives, you're going to get the regression. It's not going to be a linear regression anymore. It's going to be something more. And so I think that's my intuition about why this works so well, right? But again, take that with a grain of salt. That's my intuition, right? So I think there is still a lot of magic in these things, right? So machine learning is still somewhat magical to me. Yes. So when I say outliers, it's optimality gap, obviously. Yes. In terms of what you may have in this system is an outlier, which is like 10% of the optimal solution. And you have that even in the linear case, right? So even in the economic dispatch, you have that as well. So you may have these outliers, and we have techniques that we have a new paper on exactly that. How do you remove those in the linear case? The linear case is more complicated because the derivatives are not there, right? So, but in those cases, we have another technique to do that I have no time to present. But roughly speaking, what we have now, we have been focusing on these outliers. And when I say outliers, it's not outliers in terms of the input distribution. It's outliers in terms of the quality of the solution. So I may have misled you with the picture that I had, but roughly speaking, these are points in the input distribution for which we don't have a good solution. Great question. Thanks for letting me clarify that. Now, I have only one thing left for you. Actually, do I have only one? Yes, I have only one. I hope so. But this is one of the things that is truly beautiful. Okay, so this is like the most amazing thing ever. And so can you actually, so I told you that one of the big things that we have to deal with is storage. And obviously, here in Canada, you have been dealing this for a long time, but in most of the US, storage is like, wow, what is this thing? What is this beast? Okay, so we now have something where I can consume power, or I can generate power. And so one of the big things that it does to you is that it creates a problem where we cannot just do myopic. We have to actually look at the future. And so it becomes a sequential decision-making or a multi-stage stochastic optimization, and these problems are amazingly complicated because you make a decision, then you will observe uncertainty. For instance, when we work with Brazil or Bolivia, they will have to estimate how much precipitation is going to be in their big reservoir. And then you have another decision that you take, and then another observation, and so on and so forth. And these problems are very difficult. Now, in optimization, one of the ways we do that is by using techniques invented by this person, who is a Dutch mathematician called Benders. So he wrote this paper that everybody ignored for a long time. And in the last 10 years or 15 years, this Benders decomposition has become kind of used everywhere. And now it's called stochastic dual optimization, dynamic optimization. And so really the way this is done in practice is that you solve a lot of two-stage Benders problems, but you go down a particular scenario tree and then you go up and so on. It's a beautiful algorithm. It works for convex problems, but it's very computational demanding. And a few years ago, there was an amazing paper by Murphy and Jim Lutke in Wisconsin saying, well, but we can actually try to replace some of these uncertainty by kind of decision rules. And they put these linear decision rules inside the optimization problems, and they were using Benders on top of that. But what I want to do is actually using some inspiration from that paper, but showing you how AI can transform a multi-stage stochastic optimization problem into a deterministic optimization problem. So you move from something which is like amazingly complicated to something using machine learning, which is kind of deterministic and easy to solve. That's what I'm going to show you. And so I'm going to play a number of magic tricks. All right? So this is my single period optimization problem. And I'm going to abstract everything so that you understand it. But roughly speaking, we have a state. That's like, let's say, the state of my batteries or the state of my hydro reservoir. I have uncertainty that I'm going to observe at a various point in time. And then I have some action that I take in. This is Y. And then I have some physics and engineering constraints. And X, obviously, is going to be the next state. Right? So this is what I'm going to optimize. I have to optimize my action. Given the uncertainty that has been released, obviously there will be uncertainty for many, many, many periods afterwards. And I have this physical and engineering constraint at every stage. So that's just a single period. You have to do that for multiple periods, and then you have the expectation on all the uncertainty. So this is my problem, multi-stage. I'm giving you only 3 stages because my slice is too small. But roughly speaking, you see the first stage there. I think I have some animation there. Yes, so you are going to decide what is this state. These states are going to be there, and you're going to decide based on the uncertainty that you are revealing what these actions are going to be so that you compute the next state, and so on and so forth. And you have this knowing thing where you are minimizing expectation, then minimizing expectation, and everybody hates that, right? And so the magic trick, and so you see the x2 multiplying by x3. So now I'm again assuming that I will have a crystal ball. Okay? And my crystal ball is going to, given the uncertainty, predict my state at every point in time. Given the uncertainty up to a certain point, I'm going to predict the states at the next point, and so on and so forth. Okay? And so if I do that, I'm basically now have a machine learning model, which given the observation that I have there is going to predict my state. And then observation there, I'm going to predict the next state. And observation there, I'm predicting the next state. Obviously, when I write omega 2, I have omega 2 and omega 1 inside, right? So it's the accumulation of what happened in the past, okay? But when I do that, this is kind of amazing, right? Because the x1 variable are fixed. They are completely fixed. They are constant at this point, right? So I can remove this, okay? This is fixed. And so now if I look at this, okay, what I can do is that this problem here is completely independent of this problem there. Right? This is independent of this. There are no dependency in anything because everything is fixed. The states are fixed. And so when the states are fixed, I can permute expectation and minimization. And that's amazing, because now my problem becomes an expectation over a single optimization problem. It's a, obviously multi-period optimization, but it's a deterministic problem, right? And so this is kind of really, really nice. I have a deterministic optimization problem that I have to solve. Okay, now I need another ID. So this idea here is that I can separate. You see, this is still annoying because I have the prediction model inside my deterministic problem. So I still need to train this inside an optimization problem. This is annoying. But once again, you can see that this only depends on the observation. So I can separate prediction and optimization. So I'm going to predict and then optimize. And so in a sense, I predict, I get the state, and then I have this optimization problem, which has the structure of my single period optimization, but it's a multi-period optimization. But it's a really nice optimization problem that in optimization we all like, because everything that has been nonlinear has been removed, except the nonlinearity of the constraint, physical and engineering constraints. And then, there is no expectation anymore, right? Nice trick, right? And so the only thing that I have to do is, obviously I'm cheating a little bit all the time here, but the last thing that I need to tell you is that my prediction is not necessarily correct and may not correspond to I may not find decisions for those. So what I have to do is to say, hey, I need a recourse for fixing this such that the whole thing can be actually, realized. And what I do is that I penalize inside my objective function the difference between what I'm predicting and the decision that I'm going to take. So in a sense, you can view that as a projector layer again. I want to basically make sure that the decision that I take is feasible, and I'm minimizing the distance compared to that decision inside my objective function, in addition to the objective function that I'm minimizing. And this is a very high coefficient, such that I'm really sticking to what I'm predicting. Okay? Again, this is deterministic. And then I can do self-supervised learning, right? So, because this problem is very nice. So what I'm going to do is that every time I generate a scenario, I'm going to basically solve this problem here, which is a deterministic problem. For every scenario, I'm going to do that. So think of that. So for those of you in machine learning, is that I'm taking my mini batches. I take one of these scenarios, I solve it. I take the next one, I solve it, and so on. And then this is my forward pass. So my forward pass is like solving this deterministic, generating, predicting, and then solving this optimization problem, right? That's what I do in the forward pass of my differentiable program. And then in the backward pass, this is beautiful. This is the most beautiful thing ever. I have a dual variable for this thing, right? And so the only thing that changes, right, from the optimization problem to the other one is the prediction that I'm making. The prediction is the right-hand side of a variable, of a constraint. So I have a dual variables there. And that dual variable essentially is a sensitivity. It's like a gradient, right? So when I teach linear programming to machine learning people, I tell them, hey, the dual variables are really gradient. And so this is a gradient. So I can use this for actually doing the backwards propagation, because I basically differentiate with respect to this, and that gives me the lambda there, and then I propagate that through the neural network. So my forward pass is predicting, solving the deterministic problem. My backward pass is using the dual variable to backpropagate. Amazing, right? At inference time, the only thing that I have to do is predict using the model and solve a deterministic optimization problem. Much easier than doing multi-stage stochastic programming using stochastic dual dynamic programming, right? I'm just solving one deterministic problem, a single one, okay? And so a case study, hydropower, this is the second stage of something like what they do in South America. They basically, the uncertainties on the precipitation and so on, they control the hydropowers that they have. They can decrease, they can decide when they actually use the hydropower. The rest is a typical power flow, AC power flow. And so I'm going to show you the results, which are kind of interesting, right? So if you do stochastic dual dynamic programming, you can only use convex optimization, right? And then you have to take that solution and translate into an AC solution. So I'm going to show you what that does. So this is the stochastic dual programming using a linear approximation. You get an optimality gap of about 7%. When I say optimality gap, it's compared to the best solution we know, which I'm going to tell you in a moment what it is. And this is the time that it takes, in minutes, so it takes a long time. This is when you do linear rules, so very similar to what Jim and Murphy have done at Wisconsin. And because of the nonlinearity and the fact that you are actually using, this is an AC problem, they have an optimality gap of about 6%, which is kind of very significant in this particular test cases. The training time here is very fast. It is reasonably fast, but this is in execution time. It's like 0.06 minutes. Okay, so it's like in seconds. So it's nice. It's very nice, but the gap is big. So this is when you do stochastic dual programming using the second order cone relaxation. So you can do stochastic dual dynamic programming using the second order cone relaxation. Then you have an optimality gap of 0.32%. It's very good, but you take about 480 minutes to do that. Okay, and then this is what we do. This is what I've shown you. We have an AC solution. We have the best solution. This is we have found the best possible solution. I'm not saying that is optimal, but because this is an AC problem, multi-stage stochastic optimization. But this is the best solution across all the methods. The training time is about 60 minutes, and this is the execution time. So orders of magnitude improvement in speed at runtime. Okay, so this is real time essentially, and the best solution across all the techniques that exist. So this is how we do essentially multi-stage stochastic optimization by a combination of AI and machine and optimization. Yes?
Just for precision, what is like the scenarios? Is it short-term duration planning or longer reservoir water management?
Yeah, so they do that on a weekly basis with many scenarios. Okay. So for them, the speed that they want, in speed because they explore very many scenarios about the precipitation, and they solve many of these problems have many different scenarios. It's weak, and it's at the weak level. It's not at but they solve this almost every day. So that's my understanding of how they do it in South America. So it's solved almost every day, but for a long-term horizon, very long-term horizon.
It's long-term water management problem.
Yeah, it's a long-term 100% problem. The key point is that you can apply this to batteries. Yeah. You can apply this to batteries. And we can apply that to batteries because this is very fast. You had a question there? No, I think so the question is that, is it a two-stage? No, it's like 24 stages. It's a really massive problem. It's a very difficult problem, yeah. Because it's like at the week level or the month level for managing these reservoirs. The question is that how do you use this? Is for taking the first action, yes. And then you will observe what happens, and then you generate the next action. But it's also for managing risk. One of the big things is managing risk for them, right? Many of the things that you see in this presentation is about managing risk. Okay, good. Now, I lied to you. I told you that there were 6 images, but there is another image that I want to talk about. Okay, since I have a little bit more time. So this is the next image, okay? And so you will have to remember this. Since this is the last thing I'm talking about, you will remember it. But I want to change gear completely, and instead of talking about how you manage the network, I want to look at what the producers and the consumers are doing. So I want to talk about bidding. I'm going to talk about bidding in electricity market, and I want to do what is called decision-focused learning, and this is, again, an interesting story in differentiations. So what I want you to understand is when you bid in electricity market, you have to actually estimate the price of the market at different points. And if you are the owner of battery, which is what this is all about, you have to decide when you charge and when you discharge the battery. And so what I'm going to show you is a first solution using the implicit function theorem. And then I want to talk about primal proxies. And then I want to talk about dual proxies and how you can use them in bidding. Okay? So in a sense, what you can see here is that I'm putting a lot of things together that you have seen before for actually bidding in electricity market. And the motivation here is that what typically people do when they have prediction and optimization is that they first do prediction and then they optimize. And so when you do prediction, what people typically do, and if you want to predict the prices in an electricity market, you are going to have a data set from the past, and you're going to try to predict by minimizing empirical risk and trying to get the best prediction possible with respect to this. And what I want to argue is that this is terrible. And this is terrible. I mean, I'm exaggerating. I'm always exaggerating, right? So I'm an optimizer, so I'm always exaggerating. But what you're doing here is that you can have a model which is actually super good for things which have no importance and bad for things which are terribly important. And so what you really need to do is that you need to predict, but based on the downstream decision through the optimization problem. And that's what we call decision-focused learning. And so what we want is to actually learn this thing, learn this model for predicting the price based on the entire pipeline and the optimization. So what I want is that the predict and optimize, I want to predict, the value of my prediction here based on the loss of the optimization problem. And so what I mean by that is that if you have a prediction and you solve the optimization problem, I want to compare the value of the optimization problem compared to the value of the optimization problem if I had an exact, crystal ball to guess the price. And so I'm not trying to tune this model based on how close I am with respect to the prediction. I'm looking at how close I am with respect to the decisions of the optimization problem. And that's a completely different ballgame. Okay? Yeah? All right. So I need to, but I will again need to backpropagate through the optimization. And so this is something that we have been doing for the last 3 hours, right? Okay, so bidding. So these are some of the companies we have been working with, and I can tell you this is amazingly complicated. But I'm going to talk about the Belgian market because somehow I like Belgium a lot. And so this is how it works in Belgium. So you basically, and it's very similar to the MISO system. This is at 10 a.m. again. You close the market. You publish, the day-ahead market clearing at that particular point. And now you basically have to decide in hours of early hours, how you can bid into that market and when you need to charge, when you need to discharge for your batteries. Okay, so talking about big batteries here, and so there is a lot. Obviously, so this is batteries for regulation, and you are bidding inside the day-ahead market. The challenge is when, during that time you're going to charge and discharge. And then what you do is you need to forecast the price for every one of the periods, and that will allow you to solve an optimization problem to decide when to charge and discharge. If I knew the price, I would know exactly the same thing. There is one constraint that you will have is that you want the state of your batteries to be the same at the beginning of the various days. And so what I'm going to tell you about is decision-focused learning, and it's essentially end-to-end learning and optimization, right? So this is my optimization problem. It's actually pretty nice. This is the price. This is, I'm maximizing how much I'm selling. This is the discharge, and this is charging. Obviously, when you discharge your batteries, you don't produce everything. There is a transformation factor there that you need to compute. That's this eta variables. What you see there is that there are constraints on what you can charge, discharge. The state of charge of batteries has to be in between some ranges. And then you have the traditional constraints of the state of charge, which is like, this is your previous state plus what you charge and minus what you discharge, right? So once again, this is like a multi-stage period optimization. And obviously, this is an uncertain variable that we can predict before. Okay? So far, so good? Okay, good. So I don't know this, obviously. So if I have the prediction, I can train my network to do this, obviously. But one of the things that I want to do is obviously predict this in a global fashion. Okay? So if I want to predict that in a global fashion, what I have to do is differentiate with respect. E is this thing here. Right? So what I have to do is actually differentiate this with respect to the price. Okay? So what the decisions I do at every step depends on the price for every one of these steps. So once again, I have to differentiate through the optimization problem. Okay? So how am I going to do that? It's tough, because this is a linear program, and linear programming is really, really annoying, because we actually have this discrete gradient in a sense. So the dual variables have this bizarre shape every time you move from one vertex to another one. Okay, so this is annoying because when you try to have gradients for this, they don't mean anything when you are in those regions, right? So if I'm trying to train this thing, the gradients are discontinuous there. So what am I going to do? I'm going to ask one of my students to find a solution. And this is what they came up with, which is actually nice. So you basically approximate these things by adding some quadratic or cubic or log factors such that you actually smooth this gradient. Okay, so and so what you do is that your optimization problems become a little bit different because you have a smoothing factor there. And that smoothing factor can be quadratic or cubic in the terms of what you charge on this charge. Or they can be, and this is maybe what Andreas is going to like, you can actually look log barriers terms for actually smoothing this thing. And this is actually very nice, as you're going to see in the experimental result. So you are kind of training this in a kind of interior point method-like system. So what I'm basically telling you is that this is my decision-focused learning pipeline. I do a forecast of the price. I solve the optimization problems using the optimization problem that I've shown you. And then the next step that I do is I compute the loss using the function that I have. And now I'm starting differentiating that using the KKT conditions. And then I backpropagate through everything. Okay? So this is what I've shown you. This is my convex, this is my essentially convex differentiable layers using the implicit function theorem, and I get this beautiful thing at the end. Now, the problem with that is that I have to solve this, and again, this takes time. And so what I'm going to show you as another result is that I'm going to say, instead of solving this thing, let's learn this thing using a proxy. So I'm going to approximate, essentially, this optimization problem. And then I'm going to basically restore feasibility there and compute this thing and then restore feasibility. So this is what I'm doing here. The primal proxy is going to predict what I charge, what I discharge, given a particular price. I'm going to basically repair to get feasible restoration. I have the discharge, and then I can backpropagate through everything. Okay, so that's my primal proxy. Okay. I have no idea what this is all about, but this is nice. Oh, yeah. So this is to make sure. Actually, I don't know what this is, but this is good. This is probably to tell you that I have to restore the feasibility at the end compared to the beginning. So I've shown you this. So what is the repair mechanism? The repair mechanism is essentially you may exceed the charge of your battery, or you may you may go lower than you may exceed the capacity, or you may be below the desirable state of the battery. And one of the things that you can do is to actually scale everything like the proportional response that I've shown you before. So you can compute, how much you have to scale or upscale or downscale when you charge and when you discharge using this function. Now this is nice, yeah. Oh yeah. This is what I wanted to say. This is nice, but this doesn't necessarily restore the fact that your battery at the end of the day should be the same as the beginning of the day. And so if you want to restore this, it's a little bit more complicated because you have to write a kind of a multiple iteration algorithm that's going to scale things, but put them at the maximum and the minimum at every one of the stage, compared to the degrees of freedom that you have, compared to the state that you want at the end of the day. But roughly speaking, again, you can do that in polynomial time. What is beautiful again is that this repair layer is something that you can differentiate over. These are just kind of scaling rules for every one of the generators. Like I've shown you at the beginning. And so this is the primal proxy. But you can also do a dual proxy, which is amazing, and I'm going to show you why in a moment. So you can also learn the dual variables. And so this is my dual proxy. So this is a dual of the problem that I've shown you before. And once again, what I can do is learn part of this dual and restore feasibility. And the key point is that once you have this dual solution, and this is the amazing thing here, I have a closed form solution for finding a primal solution. And the intuition is very easy, is that the value of this, do I have this? Okay, let me see. Yeah. So the value of this dual variable there, this is the price of the value of a unit of stored energy. That's the meaning of that dual variable. And so when you look at the closed form, what this is telling you is that, if the price is lower than this, charge. And if the price is above that, discharge. And if this is in between, don't do anything. Okay? So this is kind of nice. Okay? So this is basically saying, okay, so once I have the dual variables, I can essentially recover whether I have to charge or discharge using my prediction on the price and the particular value of that dual variable. Okay? And so I have a closed form expansion, charge, discharge. These are my dual proxies. I have a smoothing step as well, because the dual proxies have this discontinuity in the dual space. You can smooth them using something which is, I think this is the quadratic version of this. This is more complicated, but this is still a closed form, which is nice. And if you apply that to the Belgian case, this is what you get. And this is kind of amazing. So this is the linear programming solver, assuming that you know everything. This is the dynamic program somewhere. It's typically very close. This is there. This is the dual this is a differentiable program. This is the dual proxies. And what you can see is that it's really, really modeling what you would know otherwise. So it's extremely nice. These are various versions that we had. And roughly speaking, what you see, and this is what is interesting here, is substantial benefit between predict and optimize compared to the decision-focused learning. So if you look at this, this is the implicit differentiable layers. You move from 0.84, which is the learning, and this is predict and then learn, to 1.46. So it's like 18% improvement. This is what you get when you use the log barriers smoothing function. It's almost as good and the exact solution using the different layers. But obviously, as I'm going to show you, it's massively faster. Instead of taking about 2 minutes, it takes about 9 milliseconds. So it's a very big difference in the speed. So this is the end at this point. So this last part was essentially combining everything that you have seen for bidding. So roughly speaking, that what I hope I've shown you is that AI is actually ready for some critical power system application. The technology there, and it's ready for some of these applications. I give you 6 images. I hope you remember them, right? So this one, what is this one? This is the quiz. Differentiable programming. What is this guy? Self-supervised learning. This one. Dual proxies. Primal dual learning. Sub or left learning. And then whatever it means to transform a multi-stage stochastic dual programming into a deterministic problem. So that's what I wanted to convey. I hope I gave you some insight of what we are doing in machine learning, AI, and optimization for a power system. It's actually a really, really nice application area. I think there is much more to do, obviously. I'm happy to take any more questions that you may have. Thank you very much.
Thank you very much, Pascal, for the presentation. We indeed have a bit of time if there's any question left, and then we'll move to a break, to the lunch break. Lunch is being currently served on the side, but we still have a bit of time. So any question from the audience? Yes, sir? No, that's you. So I'll try to use the mic this time. So yeah, sorry.
So these were all good news. Do you have an example where you thought this is a really cool idea and it should work and it totally didn't?
So I think one of the things that I think we need to do is that there are many ideas that you have seen there. And I think we need to combine them all in a complete systems, because we have done an experimentation with many of them in isolation. And so we have some techniques to remove outlier. We have some techniques for actually learning in the space of principal component. We have some of the techniques that you have seen in primal dual. I think one of the things that I think needs to be done if you really want to be super good is putting everything together. It's massive work. It's very difficult to do. I think that's what we need to do. The rewards compared to the amount of work is very substantial. So that's one of the things that I think is a big challenge. I think you want to do this because you want to remove all these outliers. And when I say outliers, it's at these points where you don't have the performance guarantees. And so I think that's one of the things that we have. The second thing is that some people want to, and I completely agree with this, and I think Spiros will address that this afternoon, is that you also would like to have guarantees a priori, which is very difficult. And so I think we made a lot of progress, and we are continuously making more progress there. But again, it's going to be, how do you actually identify systems that are going to be good, whatever the distribution is, with respect to all the points inside the distribution. And the reason why I think this is very difficult, and that's why I think I like the Sobolev training and all these things, is because it's a gigantic input space, right? So, and sampling that input space is very, very difficult, because it's, it's like, you have 30,000 buses, 30,000, input, or, I mean, you multiply that by the fact that they may be load, they may be renewable energy. It's a gigantic energy space. Energy space and also sample space. And I think we are generally safe by the fact that this is the real world, and there are a lot of correlation. But there may be outliers that we may not see. And so I think the work that I think needs to be done is also trying to generate techniques that can actually scale for actually making sure that we don't have some of these negative, non-optimal, not near to optimal results at the end. And so I think that's one of the things that I think needs to be done. And I think Spiros is probably going to talk about that. I think the challenge there is really going to scale. So I think that's one of the things that I think is interesting. And then I think the key point is that when you are in AC, it's very difficult to actually guarantee feasibility completely. The projection methods are taking time. So I think a very good direction for me, and if you're interested in working with that, you just send me email. I think it's getting much better projection methods in the worst case, because you may have to do that in the AC space. So that's what I would say is a very interesting topic. I think we have a lot of different people working on this at this point across the world, and I think that's a very interesting topic, and it's very different from what people have done in the past. And so that's the kind of things where I think it's not like you have bad news, Andreas. It's just that you have many more problems to solve, and that we have only reached kind of the top part of the iceberg. So there is a lot more things to do. Yes, sir, at the back. It's a
okay. You discuss a lot of continuous system, even when you talk about topologies was basically changing topology but still working into the continuous space. But operation is mostly about affecting the topology, taking discrete decisions that transform the system. So how far are we to have like framework that could integrate those binary variables?
So I'm going to answer your question in several steps, right? So I think the question, well, you heard the question as well as I did. So I was about to repeat a question that everybody has heard about. It just gives me more time to actually think. So I think for the topology, we have a paper that will come soon. So I think we have some new results on how to actually learn topologies in certain conditions, right? Not arbitrary conditions, but they reflect, again, the reality in the field. So I think you're going to see that. And it's also very interesting, new, very different underlying machine learning techniques behind the scene for actually learning topology optimization. Once again, topology optimization is not something that people do in real time, right? So you have to, switch things and so on, bus bars and so on. It takes time. But I think we are also completely changing the speed at which you can do these things, and people will be able to run a lot more scenarios like the real-time assessment. So I think you're going to see that up, in about, I think, 2 months. You're going to see a beautiful paper on this. I have the draft in my mailbox. So I think that's one of the things. Now, this being said, if you try to learn unit commitment, we are working on that as well. This is actually, we had a paper a few years back, but this is very different because you still want to restore feasibility globally on things that are discrete. Things that are discrete, you cannot use, in general, the differentiation that I've shown you. They are not very necessarily well designed. This is also to address Andreas' question. This is when the things become discrete, differentiation is not there. And although I have plenty of ideas, almost none of them have worked so far. So I think in this particular case, what we typically do is that we try to guess as many things as possible, and then we solve optimization problems that are orders of magnitude smaller. That doesn't mean that we can do that in milliseconds anymore. It takes time, but we decrease tremendously the space of optimization problems. So that's one of the things that we have been doing in power system, but also in supply chains, for instance. So it's a different approach because I haven't really found a really good way of differentiating two discrete decisions when they are really discrete, like yes or no, you commit or you don't commit. It's much more difficult. So I can send you some papers that we have been doing on that in that particular space. I think this is a space where we need more work. So when I try to articulate the future, what I just told Andreas and what I'm telling you are two fundamental directions that we are pursuing. Topology, in my opinion, we are in a better spot at this particular point with the new work that we have done. Yes.
Thank you very much for your lecture. I'm from Germany, and system operators there are very, very, very careful and very risk averse, and they don't really like using new approaches. So you mentioned working with a lot of industry partners. What's your experience in, maybe from a US perspective, in getting them to trust or maybe use some new approaches, especially with AI?
Yeah, so I think this is why we wrote this paper with the scientists from RTE, is to actually try to tell them, you know, we are careful. If you want to adopt an AI system, this is what it has to satisfy. I think the way I'm phrasing this, you all know what happened in Spain, right? So I think the operators now cannot manage the systems anymore. They are just too complex. They have intuitions typically that are very good for flows. When you start talking about voltages and reactive power, these are concepts that are very difficult. They are very different in nature. And they don't necessarily have the capability of having a good mental model of what that means. Some may have, but it's becoming more and more difficult. The scale also of the operations is so much bigger than before that they have issues. So I don't think, if you think about the control room of the future, I don't think you can do it without AI. And when I say AI, I don't think you want to run the so I think you need to go step by step. I think the first step is to demonstrate that this system works. And the way we do that with our partners is typically by running them in parallel to the system and showing them how close they are. It takes a lot of time. It takes a lot of energy. But I think this is very valuable because you can show impact afterwards. I think it's also going to come more in tools that are kind of telling them about the risk and so on, dashboard risk platforms and so on, before it's going to move really to operations. It's only going to move to operation when they are stuck and when they have validated the fact that we are very close to what an optimization solver would do. So I think it's a lot of building trust. It takes a lot of time. So when you do things like this, you publish fewer papers, but I think the papers are kind of more meaningful in a sense because they deal with real systems. So we have been, pushing the field by delivering test cases, more and more sophisticated test case. We were the first one to actually move from very simple test case like 15 years ago to actually things that are at scale. We continue to do that. We hope to release test cases that are going to be longitudinal very soon, which cover an entire year on the French system with really realistic time series as well. That's what we hope to do because that's also going to make the field move better. And then the operator will look at these results and say, yes, this makes sense. So I think there are essentially two approaches, working very closely with them, replicate the system, giving them tools for managing risk, which is less risky than operation, and then I think showing them results on very large-scale test cases, real data, and so on. That's the things that we are doing. It takes a lot of energy, I agree, but I think this is the only way this is going to progress because this is everything that you do on a critical infrastructure has to be tested very, very well. I think I'm in an engineering school, so we try to apply quality control, engineering principle in the way we design this AI system. Which may be very different from people in computer science. I'm a computer scientist by training, so I'm not criticizing anybody here. But I think this connection between computer science and engineering, I think there are a lot of interesting connections there that the two communities can learn from each other.
Thank you.
So maybe one last question to conclude this session.
An easy question, right?
Thank you. So you mentioned at one point the method of forecasting something and then optimizing versus going end-to-end directly into the machine learning. Yeah. Can you just talk a little bit more about the intuition, why the second way is better than
it's very, so the way the intuition is that the objective function that you use for the machine learning problem, which is typically maximizing the accuracy of the machine learning model, is not necessarily relevant. It doesn't necessarily align with the objective function of the optimization problem. And I'm going to give you an analogy, right? So I come from Belgium originally, and Belgium is a country where you have many winds coming from all kinds of directions. So, and there is also a lot of rain. And so if you want to maximize the prediction of the weather for the next day, if I tell you that tomorrow is going to rain, I'm going to be more precise than the weatherman. But my precision is completely useless for most Belgian people. Because what people in Belgium care is that tomorrow there will be some sun and I can do a barbecue. And so the key point is that you see the objective function is not the precision of the machine learning model. It's actually my high value is the ability to do a barbecue, and that's massively valued. And if it rains, if you predict that it rains, I don't care. I can't do my barbecue. I won't do my barbecue, right? So this is an exaggeration, obviously. But this is actually a real example. I mean, I would be more precise if I predict this than the weatherman in general. But the key point is that sometimes you have a machine learning. And this is happening in real life, right? So we have these people in one of the Fortune 50 company. They have a machine learning model that is amazing. They came to me as we beat all the machine learning model that people had done for us. But then we make the decision, and this decision are terrible. And the reason is that machine learning model is very, very precise on things that they don't care about. And they have no impact on the objective functions of the optimizations. That's a real example. And they ask us, how do you do that? Well, how can you do this? And so obviously there are machine learning techniques to do that when the data sets are in balance and so on, when you could put weights on different things. But fundamentally, the right thing to do is end-to-end optimization, end-to-end learning and optimization. That's like the holy grail. If you can do it, that's the best thing you can do. Obviously, you can approximate that in various ways, but this is why this is important, because this misalignment between maximizing the accuracy of the machine learning model and actually predicting the things that are really important. And that's this whole area of decision-focused learning is exactly that. It's like, how do you maximize the accuracy of your machine learning model for things that matter? And the things that don't matter, you don't care. So if you want an example in power system, there may be these small wind farms that we're going to maximize the accuracy on. And it doesn't matter. It's like, 0.1%, 0.1 megawatt, 0.1 megawatt. There is this other big wind farm, which is like 5 megawatt. And if you predict that one better, it's going to be much better. And so that's because it's at a very important place in your network and so on. That's the analogy in a power system. So you want to predict very accurately what matters. The rest you don't care. Great question. I should have used the analogy during the presentation.